Okay. Was everyone able to get the labs? No? Okay, so yeah. Yeah, so the Windows will be fine for the first lab. We can just build the flow graph that's part of the zip file. We can just build it by hand. It's a few blocks, but that'll be in the second half of the tutorial. So once you download the labs, open a terminal and type this command, IOInfo-n, and then this IP address. And you should get a response from the radio. If you can't find it, please raise your hand, and we'll check your virtual box. Plug the radio in. Yeah. You have a question? Pardon? The previous one? Yeah.
Can I just ask one question?
Yeah, sure.
Has anyone taken one of these bags by mistake? Because we're missing one bag. What? Yeah, you know the bags of the conference. Can you check? Maybe you took a bag by mistake and it's not yours. Sorry about that, but we were a bit afraid that we lost one bag, but it was put inside. Oh. No? Everything's fine? Okay, thanks. No, it was now, just now. Okay. Thank you.
It should return automatically.
So no context fan?
So -n, and then the IP address.
Okay.
Okay, we're going to get going. If you can't connect to Pluto, we'll come by and check your machine out during the lab. Yes. Oh, no, sorry. This tutorial will go through the Pluto itself, the transceiver inside of it, as well as the software and HDL pieces that are that drive Pluto and allow you to access and use the transceiver on board. My name is Travis Collins. I'm from Analog Devices. I have with me Mahai and Adrian from ADI as well. I've come in all the way from California, which is kind of a bit of a flight. And I'm still kind of jet lagged a bit. And if I kind of wander off with my voice, please tell me and I'll speak louder. Or go slower. Please ask questions. This is kind of boring for me if it's just some big monologue. Feel free to ask questions if something isn't clear or if you want to get more information. Now, just a little introduction on SDR devices. This is actually a picture of a radio that we used to bring around to a trade show itself, where you have like 5 or 6 boards, mixers up and down, mixers, PAs, LNAs, converters. And what's not shown here, besides the 5 power supplies that are driving it, are the 5 PCs that are underneath the table that are driving the solution. And you needed 5 PCs because none of the software worked. It worked on different OSs, on different versions of OSs, and it's a big, complicated device. And using this is a challenge not only for the people developing these devices, but also those using it for applications. And this is why we've built devices like the 9363, 9361 that are inside Pluto and other SDRs that you've used. Now, just a little to talk a little bit about the architecture of the transceivers themselves. If we kind of go back to the basics of radios, the most common radios for the past like 50, 60 years have been this superhead style, super heterodyne style of radio, where you have so an RF signal will come in and then go through a series of IF stages, where you might have one or two stages. And this design is big, powerful, or power hungry, but this is the kind of traditional style of radios that if you're, say, a little bit older than me, this is kind of the radios that you're used to in the past. And on the super kind of bleeding edge of radio design is this direct RF style of radio, where you have a very high-speed converter, like a RF DAC or RF ADC, that's directly hooked up to an antenna. And this is kind of the newer style of devices, but it requires very wide converters, like 10 gigasample a second type converters. And dealing with that data is a challenge, and feeding power to a device like this is a challenge as well. And just like using it from a software and HDL perspective can be very difficult. And we have this kind of third style of radio, which we call zero IF. Instead of having a IF stage, we directly mix down that RF signal to baseband, where the converters feed it in. And this is the most common style of transceiver that ADI provides. So the 9361, 71, and the newest generation transceivers all use this zero IF style, where we have a single mixer, and that brings things down to baseband. And this really hasn't been possible for, I would say, until the last like 10, 15 years, just because of there's added complexity when you have a single IF stage. You have to deal with images and DC problems that are common to this architecture. And there's a lot of pieces inside the chips themselves that kind of compensate or deal with these non-idealities that are introduced from this architecture. So these are very simplified block diagrams of radios, but really what makes them work is things like quad calibration, baseband filtering, DC correction, integrated LNAs, programmable baseband filters. So there's a lot of moving pieces inside the transceivers, which makes them super flexible, but also really complicated to use. And over the past 5-10 years, we've tried to simplify that or make it easier for people to use these devices with different layers of software that abstract a lot of this complexity away and try to manage things in a more sustainable way. Now, the transceivers from ADI, like inside Pluto, is a 9363, which is part of this kind of family up top. So we have the 61, 63, 64. And the real differences between them are reduced bandwidth or reduced channel count that you might have. So Pluto is based on the 63, which is technically 2x2. We pin out only one transmit, one receive channel, but it has a reduced bandwidth of 20 megahertz that you can receive. The transceivers on the bottom are the second and third generation devices. So the 9371, which is just like these are just more bandwidth, higher linearity performance. 75 is unique because it has integrated digital predistortion, which is the first chip ever to do that. And this is kind of a big complicated table of, this is really just talking about the differences between these devices. This is not meant to be a sales pitch or anything like that, but depending on your application, you'll use a different device. For most people, they don't need 200, 400 megahertz of bandwidth, and a device like the 9361 or the 63 that's in Puto is enough for most of your applications. And as you go up in bandwidth, you go up in power and complexity. So it's nice having the linearity performance of the newer transceivers, but there's added complexity associated with kind of dealing with that. But if you're kind of coming from I would say the more consumer end of SDRs, and you're not fully familiar with the chips that ADI provides, if you're using a device like a USRP or on the right we have a Sidekick from a company called Epic Solutions. There's a Blade RF in the middle, B-Cube, NewTAC on the bottom right. All these devices contain analog devices transceivers. So you've probably used them before, you just didn't know them. But to drive these chips, there's a lot of kind of moving pieces that are involved. And at the end of the day, it's, you'll have some hardware on the left, some HDL that will interface with that hardware, and then some software that's driving it, that's managing state, that's handling the different settings of the device, allowing you to interface with it at different levels. And then there'll be some higher level software on top that allows you to stream data back and forth from the device. But software-defined radio is kind of this, this mixture of many disciplines, which makes it super powerful, but also complicated, because you have to be an expert in RF design, in software engineering, in SoC assembly, in DSP. My background is in communications. My master's and PhD are in comms theory, so that's kind of my end of the field. But to do SDR right and to get the performance out of these devices, you really need to be knowledgeable in all these spaces, and SDR is really in the center of them. So most development of radios is really a group effort, and it's hard to be an expert in all these fields. Okay, so let's talk about Pluto specifically. As I mentioned, Pluto is using a 9363 inside of it, which is this zero IF architecture, which you have on the left. On the right is the simplified block diagram of the 9363, where we have transmit channels on, or excuse me, receive paths on the top right. On the bottom we have the transmit paths, and then on the far right we have this kind of a collection of things we say other stuff, or it's like that, the things that make it work, right? 'Cause most of us are just interested in the transceiver, but you need these other pieces to move data back and forth, to interface with the device, to configure it, to make it usable. And we'll be talking about that throughout the presentation. So who is familiar with a Zinc or a Zinc-based FPGA? Okay, so for those who aren't, a Zinc is a more modern FPGA. Zinc is from Xilinx. Xilinx makes the Zinc-based radios. The unique things about the Zinc series is that they include programmable logic as well as embedded processors, so they have hard ARM cores on board them. So Pluto has a Zinc 7010 on board, which is a pretty small FPGA, but we really just use it to interface with the device to pull data back and forth. There is some resources available if you want to do some signal processing. There's about 80 DSP slices available, and kind of you can use them freely as you want. And here's kind of the basic marketing diagram of what Pluto is, where you have transmit, receive, and USB. And that's the simplest way we can put it. But there's a lot more going on to actually make that work and move signals back and forth. And on the right, we have the board that's actually inside Pluto, where we have the Zinc that's in the middle, the transceiver on top, and then we have USB PHY, some DDR, and flash as well on board. And the device is 12 bits, both DAC and ADCs, is flexible from 20 kilohertz to 20 megahertz of receiving bandwidth. This is complex bandwidth, INQ. And then that you can stream that out over USB 2. So the device is capable of supporting the max rate of the transceiver, but not over the USB connection. So, but to be honest, like GNURadio cannot handle the full bandwidth of the transceiver. So the channel bandwidth is 20 megahertz, but the actual data rate that you can get back, that you can run the converters at, is 61.44 megasamples a second. Yeah, so and then if you're, say, pinning out both transmit and receive and both channels for transmit and receive, you actually cannot keep up with it with USB 3.0. So it's, we say that the USB 2 is fine for most people's applications. Now, one of the reasons we actually did Pluto was because people didn't believe that you could build a low-cost solution around the transceiver and around kind of our products. ADI has been really traditionally known for super high-end devices, converters, analog components. But Pluto is really a representation of a simplified design that you can build on your own. The BOM has only 72 line items, so that includes all the way down to resistors, capacitors. It's a very, very compact design, and we provide schematics, Gerbers, Allegro files online. So if you want to build your own board off of Pluto, you're completely free to do that, and we really welcome that. But if we look at the kind of system level pieces, Pluto is essentially a transceiver, FPGA, and the pieces needed to run that FPGA. And Linux runs on board. So you can SSH into the board. It has a UART console that comes up automatically. And then there's obviously DDR, SPI flash, and then power provided on the board just to get things going and to make the processor usable. But compared to, say, other devices that we've had in the past, on the left is a more traditional, I would say, eval system that ADI would provide, or even some of our competitors would provide, where you have a FPGA eval system like a Z board or a ZC706 or like an ultra-scale variant, and then you have a FMC card that hooks up to that. And this is really what people would take into the lab, do development on. And then we have on the right more integrated solutions like Pluto. We have also the Epic Sidekick, which is one of our partner boards, and also these system-on modules, or SOMs, that we also provide, and these are designed to kind of build around them, so they don't include front ends on them. They're modules that you start from, and then you add the additional pieces for your own radio to really simplify the development process for you. But if you look at the kind of block diagrams, they're pretty much identical. They all have a transceiver, FPGA, and some connectivity off the board to allow you to control things from a remote computer or some other base device. Now, Pluto is a little unique. When you plug it in, it will show up as 4 devices. One is mass storage. The mass storage includes some basic information, as well as like the info or some configuration that you can control. So I have Pluto hooked up right now, and get my mouse. If I go to my this PC, you see that I have a Pluto mass storage device right here. If I click on that, there's a few files on board the device. There's a config file, and this will include information for setting up the network configuration. If you want to plug in USB dongles for Ethernet, Wi-Fi, you can configure those settings from this configuration file. You can set up some additional diagnostics if you want to run that on Pluto if something isn't working as you expected. And then we also have these web pages that contain a lot of valuable information that will tell you how to upgrade the firmware, where to get drivers from, where to get the software libraries to interface with the device, some basic getting started tips, IOInfo, which we'll be going into in the lab, and then different frameworks like MATLAB, GNURadio, some other tools that ADI provides, and just basic information if you're just starting off and want to learn how to interface with Pluto. It's all available on board. Now, besides the mass storage device, it also shows up as a serial device, so you can access it over UART, as well as an Ethernet device, which is a little weird because it's connected over USB. If I go to, let's see, ipconfig, because we're on Windows. Let me make this a little bit bigger so everyone can see it. Okay, CMS. Okay. ipconfig /a. spending too much time on Linux, forgetting all the commands. So Pluto will show up actually as an Ethernet device. Right here. And one of the reasons we did this is for virtual machines. Whenever you set up a virtual machine, they're always going to have networking working. It's just the first thing you need to do, apt-get install something. And USB can be a little bit on the flaky side in general. So network is an obvious thing to have on the device. And this works through a tethering protocol called RNDIS. This is actually a Microsoft standard and is available in the Linux kernel as well. To get this to work on Mac OS X, requires a little package called Horrendous. A little play on Horrendous. And that will allow you to get network connectivity if you're on a Mac, which is just a little kind of quirk because Apple is not going to implement a standard from Windows on their machines. Okay. Are there any questions so far? Yeah.
But the mass storage is also used for the firmware update?
Yes. Yeah. So you can drop firmware files or even the entire zip file that contains like some of the other like debug boot files we provide, like the JTAG boot files, the DFU files. You can simply drop that on Pluto, eject it, and it'll update.
The zinc will boot from the serial flash then?
The
Zinc, there's some state embedded in the serial flash.
Yes.
Boots the zinc then?
Yes. Yes.
Okay.
Yeah. So you can't boot from the mass storage device.
Mm-hmm.
You have to write to the flash on the device to do that.
Yeah, all right.
Okay. Now, one thing that's also unique about Pluto is that it has two USB ports, and this is kind of confusing for a lot of people. Pluto has the ability to use OTG USB devices or on-the-go USB devices. So what we can do is I can take Pluto, I can plug power into the leftmost USB port, and that will just power the device. And then I can plug in a USB dongle, like a Ethernet device, Wi-Fi dongle. We can run scripts from USB devices as well. If they have this special name, run me, on them, Pluto will just run them automatically. And this is great for doing captures standalone. You don't need a PC connected to it. There's actually a little button. There's actually a little button on the bottom case, which you need like a pin. Okay, there we go. So the button can actually be used from by the user for different things. If you want to, run an action based on that button press, you can do that. A lot of people will connect to like a USB mass storage stick, and then walk around and push the button and do captures based on some, localized information that they're looking for. So obviously, you can connect it to a Linux machine, Mac machine, Windows, Raspberry Pi, across the board, pull data back and forth, configure the transceiver. You can plug thumbsticks into it. This is one of my favorite thumbstick images. Very accurate for what it is. You can also plug Ethernet dongles into Pluto, and they'll take the IP address that's in the configuration file on board. If you want to put it on top of like a mast or like on your network somewhere, you can access it over that Ethernet context, and instead of having it connected to directly to your machine, which a lot of people do. We also support Wi-Fi dongles. Most major dongles that are supported in the kernel, we pull in and we can use. We have a list of known working ones that we've tried, which I wouldn't say is super extensive, but it's what we have around the lab and what's most commonly used by our engineers. One little experiment that we've done is actually hook up a pair of USB speakers. This actually required a change to the kernel that's on board just to enable this functionality. if you want to do this on your own, we do provide all the instructions needed to build the kernel, to modify the kernel, to build the firmware images if you want to do that on your own, to change the HDL if you want to do that on your own. It's a completely open platform. It's really designed to kind of allow people to tinker and change things depending on their use cases. But from ADI's perspective, Pluto is really not that different than like our traditional eval boards. 99% of the HDL that's on this device is the same that's on the SOM device, which goes for $1,000. It's the same HDL that runs on our ultra-scale platforms. So once you kind of learn what you're doing on this device, learn the software layers, then it's pretty trivial to move to these other higher-end devices, more higher channel count devices, which might be a little bit friendlier on your budget. So you start with Pluto, learn what you're doing, and then kind of move on once you're ready and you need the FPGA resources, or you need a more higher-end transceiver or high-speed converter, something like that.
There's no standard DES interface for ESD, ADCs, and DUCs, and the Zinc.
So you would have to build your own board to get that. Yeah. Okay. Are there any questions so far? All right. Haven't lost anybody yet?
Is that available?
Yes. So I'll post this on the same webpage that you grabbed the slides from, or from the labs from, a PDF for the presentation.
Thank you.
Yes.
Couldn't find the button.
So there's a little hole, like it's on the bottom. Yeah. So it's right there. It's a little pinhole. Yeah. Yes.
If I plug a new Wi-Fi module, what can I do with it?
So you can connect to the device remotely. If you want to, if you connect the Wi-Fi module, you can enter that IP address into, say, the GNURadio block, and you can stream data directly from it. Yeah. I wouldn't totally recommend doing that. The latency will be bad. The data rate will be very inconsistent because we can saturate USB 2 like easily, USB 3.
The RX filter is okay? The language filter?
Yes, so the 20 megahertz limitation comes from the front-end analog filter that's on the transceiver. There are no external filters on the board itself besides the balun, which if you're building a product, you need filters out front. Later on, if there's time, we can kind of talk about some reasons why you might want to do that. There's some pretty strong harmonics that come out of the device, just comes out of the architecture of how the transceiver is built. But if you're building a product around the transceivers, you need analog filters. If you have a radio from, say, like Edis Research, you'll see a big filter bank sitting on the front of the radios. Yeah, so one of the reasons we don't provide them is like they're expensive because you need a filter that's over 70 meg to 6 gig for our transceivers. So it would be big or really expensive.
What about the maximum speed in Wi-Fi connection? Wi-Fi? You have tested?
So it depends on like Wi-Fi. You're super dependent on the network that you're in. Ethernet, we found sometimes can be better than USB, than serial, just because the network stack is more optimized than serial interfaces are.
Because you connect a USB 3.0 to Ethernet converter.
Yes. Yeah.
It's going to be gigabit.
Right. Yeah. Yeah. So you're always going to be limited by USB 2, and no matter if like you had 802.11 AC dongle hooked up. So.
But sometimes I found that if you use packets,
Mhm.
they break.
Oh yeah. Yeah. Because so I/O isn't really designed for a contention-based network. It's more like you're directly connected and you're pulling data up high speed. So.
One last aspect.
Yes.
I couldn't help notice the MATLAB logo down there. How
Yes.
are MathWorks and analog devices connected?
Yes. So we work very closely with MathWorks, just because a lot of our users use MATLAB, use Simulink to do a lot of their development. So personally, I used a lot of GNURadio during my PhD. I'm the maintainer of GRIO. If you're familiar with GRDOA, which is the DOA open source or out-of-tree module, I'm one of the co-authors of that. So I did a lot of like phase array, things in my PhD using GNURadio. But depending on what you want to do, you know, like honestly, everyone starts in MATLAB to build their algorithm, and then they move it into GNURadio. It's just, that's how it works. And we work closely with the MathWorks because we provide interfaces into MATLAB and to Simulink, because that's what our customers ask for. And we build tools in MATLAB and Simulink because that's what, it's the more ideal tool for those things. If you're doing analysis, it's kind of like the default tool for a lot of that stuff. But, and you'll see the MathWorks logo in some of our slides just because we do a lot of presentations with MathWorks. We do a lot of trainings with MathWorks. We have targeting support if you want to do HDL code generation from those tools. We have automated ways to do that. Yeah, just to kind of mention that. Are there any other questions? Yes?
About the track, to have a wider coverage, what are the problems with it? And
Yes, so the hack that we have online to extend the range. We get a lot of questions about that. So the difference between the 9363 and the 9361 is the RF bandwidth, so that front-end filter, as well as there are some other features of the transceiver that we don't give you access to, like multi-chip synchronization is not included in 63, as well as I don't think LO, external LO support is provided in as well. So what, during tests, we don't guarantee that the part works over that entire range that the 61 is validated over. So if you don't get the data sheet performance at those lower frequencies or higher frequencies, then yeah, that's just unfortunate for you. But the chip's not guaranteed to work over that range. So that's kind of the extent of that. Internally, we tell the driver that it's a 9364, and then it just moves over that range. So it's just, the chip might fall over at those lower ranges. Okay, so let's move on and talk about the software stack that we use to interface with these devices. So we use this, this software layer called the industrial I/O layer. I'll kind of talk about how it's structured and how we use it. This is not an ADI thing. This is a infrastructure piece that's within the kernel itself. We use it, our competitors use it, and a lot of people across the industry use it for different things. Again, this diagram will kind of show up a lot through the presentation. It's the simplified 9361 transceiver diagram. But you can see that there's a lot going on. And this device has over 1,000 registers that make it work. And we really say that's 999 ways to get it wrong. So there's a lot of HDL and software that make the device work. Now, I'm going to be kind of building up how we talk to Pluto and how we talk to the transceiver in this diagram. This is a more system-level diagram, where in the middle we have the Zinc, on the left we have the transceiver itself, and on the right we have a host PC that's running GNURadio. It could be running MATLAB or Python or some of the I/O tools that we provide as well. But I just want to give you a high-level perspective on how things are working. But on the far left, this doesn't have to be a transceiver. This could be high-speed converters that we support, as well as even like sensor devices like IMUs or amplifiers or okay. Oop. Python, thank you. Okay, close that. Okay, there we go. All right. But I just want, from this kind of section, I just want you to get this perspective on this common interface that we use to talk to our devices. And this allows you to kind of move across different transceivers, different converters, different sensors. And you can use them all through GNURadio, so through the GRIO AutoTree module. So if you have a device like ADI has, we support over 800 different devices through I/O, as well as some of our competitors. And you can use those blocks or those devices with our blocks. Now, the subsystem that we use in the kernel is called the Industrial Input-Output Framework, or IAO. And this is really designed for ADCs, DACs, sensors, accelerometers, gyroscopes, kind of low-level pieces that don't really fit into, say, like the input framework that's in the kernel, which we typically use for like mice, keyboard, those type devices. IO has this very hierarchical structure, where at the top we have a context. A context will be a board like Pluto, or it will be a like an eval kit with an FMC card attached to it, and that will have a number of drivers or physical hardware pieces that are associated with it. And a context can be local or it can be remote. So Pluto is actually a remote context when you're accessing it from your local machine. And then, so just below that context will be a collection of devices, and these are like essentially just drivers that are associated with an ADC or DAC. The transceivers themselves will have 3 drivers associated with them, one for the transit path, one for the receive path, and one for the main control plane. That will be common attributes between transmit and receive. Like sample rate is a common attribute that's shared. The devices will have these attributes, which will contain things like LO, sample rate, filter settings, automatic gain control settings, all the knobs that you want to get at. And then at the bottom we have our I/O buffers and channels. And this is how we're moving data back and forth, how we're pushing data to the transceiver, pulling it back. And these will have attributes associated with them. So they'll tell you, like, here's the data type, is it signed, how is it shifted in the buffer, all the things that you need to kind of understand what the data format is and to move it back and forth. From the perspective of the driver itself, if you want to access the IAO driver, you can do that by going to sysbus IAO and then the device on the physical board. So you have to be physically on the device or SSH'd into the device that that hardware is connected to. And we can do things like look at the name of the device as well as echo and cat into the file descriptors that are part of the sysfs for the driver itself. So the attributes will show up as files in a set of folders, and that allows us to interact with different settings of different devices. And here we're just changing a gain setting of the amplifier. And we can cat out different settings so we can know what the current setting of the device is. A unique thing about I/O is that it tries to keep things in a human-readable format or standard units. Typically, if you look at a data sheet or a user manual for a device, you have to kind of take the register and then figure out what that actually means in real units. And I/O tries to abstract this to common units like dB or watts, amps, these type of things. So it's a lot easier on the user to use things. Now, this driver, as I mentioned, is living in the kernel on the device that that hardware is connected to. So this is in the kernel of Pluto itself. And this is controlling the transceiver and moving data back and forth. But using these attributes is a little non-ideal because you have to SSH onto the board, cat echo all the settings that you want to change, which is great for a driver maintainer, developer, but for a user, it's kind of painful. And just to give you an idea, for 9361, there are over 200 attributes that are associated with the device. So you have a lot more than just LO, bandwidth, and gain. There's a lot more settings that you have access to. The AGC alone has over 52 settings. So lots and lots of configurability. But they're provided through I/O if you want to get to that low-level access of the device.
You just mentioned gain, setting gain.
Yes.
What kind of loop bandwidth would be unachievable if you do automatic gain control using a bash script? Or is this...
It's
not the recommended way, I think.
right. So if you have very tight tolerances on timing, you need to do things on the FPGA.
Yeah. Okay. Right.
Yeah. Okay. Now, to kind of help this problem of interacting with the sysfs, we developed something called libIO. or the libIO, which is a user space library that simplifies the interface to using these attributes in dealing with these buffers. libIO is a C-based library, and we have bindings for C, C++, C#, MATLAB. There are third-party bindings that include like Node.js if you're a Java developer and you want to kind of add Pluto support or libIO support into your web application. You can totally do that. And we obviously have MATLAB support for connecting to devices as well. And they all have this kind of common infrastructure or common API where you create contexts, which is a device, and they'll have a set of physical or drivers that are associated with physical devices. And this allows you to simplify the interaction with I/O and to provide error checking and all the kind of the niceties of a library to interact with a device. But we're still running on the device. This libIO library is running on Pluto itself and is just interacting with the low-level sysfs or I/O drivers. To help with this, we added this feature called remote backends inside libIO, and this allows you to remotely access these attributes and these buffers from a host machine. And this could be done over USB, over a serial interface, PCIe, Ethernet, and it works in this way where on the right here we have a host or a device like Pluto, which has a I/O device associated with it, like the transit path or the receive path, which is inside the kernel. And then we have libIO that's running on the board itself. Part of libIO is a little daemon called IOD, and that will allow you access to this driver remotely. And then we'll have an Ethernet connection, a serial connection, a PCIe connection for high speed. And then on the host machine, we have the same libIO library that's running, and this is what GNURadio is using. This is what MATLAB is using to talk to the radio itself and to translate commands back and forth. You can think of it as a RPC, a remote procedure call, if you've used those in the past, with buffer capability, and can be used locally or remotely. What's really great about how I/O is written, or libIO is written, is that you can write code on your host machine, define a remote context, say IP this number, write that code, make sure it works, and then copy it over to the device itself, change the context to local instead of that IP-based one, and run the same code. And it's a really kind of nice development style. And you don't have to reinvent that code if you want to move it to the embedded platform. But as I mentioned, this is really the kind of the low-level pieces that GNURadio is using to interact with a device. So if you take our generic blocks that are in GNURadio, you can use them to add additional settings that might not be in our Pluto blocks. So if you want to change like some bizarre setting that's in the AGC that no one would want to change, but you want to do it, you can do that through our more generic interfaces in GNURadio. And it's a very kind of extensible way to get at the driver. And that fills out our picture fully now here. So just to kind of repeat the data flow. So when we get data from the transceiver, it goes through the FPGA, then it comes into the I/O driver that's in the kernel itself, goes out to libIO, talks through that daemon that's running on the board, and then that will throw data back over TCP/IP, over serial, over PCIe, back into our host machine that's running GNURadio or some other software application that's using libIO. Okay. Is that clear? Yeah? Any questions? Okay. So this could be a Pluto device, one of our system on modules, which have like an integrated transceiver, FPGA, or an eval system. Yeah?
The IOD,
Mm-hmm.
can we use it to transfer? I mean, running standalone the board, and also use the IOD to send data to at the same time, or?
So like, you mean like send data back to the host machine?
Yeah.
No. So you can't like insert stuff into the layer. You would have to modify the driver to essentially do that. It's really not meant for that purpose. But with any good library, there's a set of command line tools that we can use to interface with it directly. For I/O, we provide a number of these. The first one at the top is IOInfo. This is great for just finding a device that's connected to your local machine. Unfortunately, on the Linux VMs, it's not connected through as a USB device. It's only connected as Ethernet. And you can't actually, by default, Ethernet devices are not what we call discoverable. So scanning does not apply to Ethernet devices. If you know the IP address, you can simply just provide the -n flag and then the IP, and it will look up that device for you. But if you're on a host machine and you have Pluto connected through to that OS, I can open a terminal or a command prompt. And I can just type IOInfo -s, and it will find Pluto for me. Yep.
You said that there is a hundred of parameters within the transceiver, but where is the tool that helps to choose the right one?
Yes. So the
Within the library?
that's choosing the right attributes, or
The right parameter for the
yes. Yeah. So the driver will have. So the driver just represents like different settings of the device as attributes to you. So like automatic gain control will have, say, 3 modes. One is manual, one is slow attack, one is fast attack. If you provide it like like hyper attack or something like that, it will error, but the device won't fall apart. So it helps you not configure the device in an incorrect way, and you don't have to go down to the registers, and you don't have to understand how they work. Yep.
Yes, you mentioned before that it's possible via USB on the go.
Yes.
For example, USB audio device being attached to the middle port when you power it from the other side.
Yep.
But that means that there are isochronous endpoints on the USB controller.
Mhm.
Would it be possible to use isochronous as communication for the RF data between Windows application or GNURadio and the Pluto SDR? Because then you could probably have more latency because you can use that USB. You don't have all the caching and TCP/IP overhead.
Yeah, so if you use it as a serial device, not TCP/IP, that's what it will do.
Oh yeah, all right, serial device. And,
Yeah.
Okay, well, but it's still using built endpoints, not the isochronous.
Yeah, so I think the RNDIS driver does that for you in a kind of optimized way.
Okay.
Yeah, yeah. So the serial to network like emulation is designed for tethering.
Okay.
So if you had like a Windows phone or an Android phone,
Yeah, I get a PPP or some other serial thing.
right? So and people are usually concerned about performance with that. So RNDIS is pretty good. Okay. But if you kind of want to go a little bit beyond just command line tools, we do have an open source application called IOScope. And this is designed for debugging, visualization. A lot of people use it for evaluation purposes of the transceiver. It will expose all of the settings for you. And there's hundreds of them available. The application includes time domain, frequency domain plots, constellation plots, a lot of markers, a lot of measurement tools that you can use. And it's completely open source, so you can modify it, add plugins if you want. For each device that we build, like the transceivers or high-speed converters, we have specialized plugins that present their attributes in a kind of useful way. But if you want to modify it for your application, say you have a custom driver that is IO-based, you can use that in this tool. A great example is on my Linux laptop, the gyroscope driver that is used to rotate the screen if you rotate the laptop shows up as an IO device. And if you open IOScope, you can actually pull out the gyroscope data from that device, which is pretty unique. Okay.
Is it a command line or is it a graphical GUI?
It's completely graphical. Yeah, so this tool is graphical. Now I'm just going to go into using some of the IO tools just to give you an idea what it's like to use them in IOScope. And then the lab that we'll be doing will start off with the low-level command line tools, interface with the radio, and then go into using IOScope and pushing data back and forth. And then the second lab will show how we can kind of translate that into GNURadio. Okay, so back to the command line here. I have Pluto connected. Is that text big enough? Can everyone read that? I can increase it? Make it bigger? No, it's good? Okay. As we can see here, IOInfo is great for scanning for new devices. If we have, say, an Ethernet-based device, like Puto is only represented as an Ethernet-based device on the VMs that you're using. To see if it's attached, what you can do is type IOInfo-N and then the IP address. By default, it creates an Ethernet device under so the local Ethernet device that will create will be 2.10, but the IP of Pluto itself will be 2.1, okay? And then it will go out and actually pull a bunch of attributes and tell you all the attributes that are available on the device. And as you can see, there's like a lot. It just keeps scrolling and scrolling and scrolling. Okay. Now we'll clear that. And the other really useful tool is IO attribute. And here I'm just going to use the -A flag. The -A flag will connect to the first context that it finds. If you're on a Linux machine, a lot of the times you'll have IO devices on your machine. So the -A flag is not always going to pick up the radio. It's going to pick up the gyroscope or a backlight keyboard or whatever IO device that you'll have. So if you're using -A, just be aware that that can happen. And since I'm on a Windows machine, there's no Linux kernel, so there's no IO devices, and I can use that. And then I'll use the -D flag, and that will list the drivers or the IO devices that are available on that as part of that context. Do -D, and we can see that there's 5 devices that are associated with Pluto itself. So the ADM1177 is actually just a power monitoring chip, and we can pull out instantaneous current and voltage from that. The 9361-PHY, so this is the main control plane driver for the 61. The same driver is used on 61, 63, and 64. And this will contain the shared attributes between transmit and receive, so like sample rate. So we'll don't try to copy all the commands. I just want to give you a sense of what it's like, and in the lab we'll kind of go into these things. Okay. So the third device, X80C, that's actually the ADC that's on the FPGA itself. So if you, I believe almost all of Zinc FPGAs will have an X80C on board. There's an IO driver for that. The bottom two, the CF-AD9361 DDS core LPC, great name, is the transmit core. And the reason it has DDS in the name is because there are DDSs that you can use in the FPGA. And these are available through IOScope, through all the attributes. Technically, you can use them also through GNURadio as well. LPC is in the name because the FMC card that's associated with the 61 is a low pin count connector. When you move up to our higher end transceivers, they'll have the extension HPC, and that just means high pin count. The bottom driver is for the receive path, and it's just that will contain the receive buffers for the receiver. Okay. Now what we can do is we can list so that was the -D flag. We'll use the -C flag to list the channel attributes of a channel. And I'll type in one of those drivers that we saw on the previous screen. So the channels that we have available to the main control plane are voltage 0, voltage 2, voltage 3, and these alt voltages, which are actually for the LOs themselves. And then if we simply add that to the command, so I want to look at the channel voltage 0, here's where the additional attributes will show up. So we have things like the quadristor tracking enable is done here, the RF bandwidth, the DC tracking, sampling rate is changed to these attributes. So you can use IO attribute to individually change settings. You can create a bash script around using this tool to set up a device in a programmatic way. And it's really useful for just poking at little things or changing one-off settings or scripting things. Yeah?
All these attributes are the same in all type of codes, like in buildings, MATLAB, or C.
Yes.
Call it and you can use it.
Yeah, so if you, so the API that exists in those tools might be slightly different, but as long as like you have access to the bindings, then you can edit any of these attributes. Now, so these are the standard attributes. What we can do is also look at what we call the debug attributes, and those are the more complicated ones, or like there'd be dragons here. I wouldn't play with them. They're more advanced settings that most people don't really have to get into. And you can access those by just using the uppercase D flag, and that will list the debug attributes. And there's a lot of these. They just keep going and going and going. So, but you really shouldn't have to get into these unless you're really tuning the radio for a certain configuration that you need. Okay, so command line tools are great and all, but if we want to get some real work done, we might go into a GUI application to visualize some signals. And for that, we can use IOScope. Okay, so now IOScope supports Windows, Mac, Linux. So if you we have binaries. If you have a Windows machine you want to run it on, the first window that will show up when you launch IOScope will be this connection window here, and that will allow you to connect to different contexts. We run IOScope on like the Z board, the ZC706, the ZC102.
It's a Windows application.
Yes, so it's a Windows, it's a Linux application, it's also a Mac application. I'll show you how to launch it on Linux when we begin the lab. Now what I'm going to do here is just select the remote device, the network context here, type in the IP address of Pluto. I hit refresh, and it populates those IO devices that we saw before with that IO attribute command. Okay. I can also select USB devices, and you'll see the same IO attributes. I'll hit OK, and it will bring up a capture window. We'll go back to that, and a control panel here. And this control panel is used for configuring the transceiver, setting up different modes. There are two main panels that are associated with 61, 63, 64 base devices. And they come under this FMCOMS 234 and FMCOMS 2345 advanced tab. On the newer releases of IOScope, this will say AD936X, so it's not as confusing. But the reason that name exists in my version of IOScope is because FMCOMS was the first generation of 61 eval boards that we provided to people. So that's why all the tabs are, in a lot of our original documentation, will all say FMCOMS. They won't say 9361, just because it was the first generation, and it's just the names have stuck around for a while. Okay, now the advanced tab, we really won't get into that just because it's kind of, yeah, sure, yeah. Can we shut the door possibly, or maybe not? It's a little hot. Okay. So I'm just going to go into the main panel here, the FMCOMS 234, and this will contain settings for the both transmit and receiver. On the top panel, we have the global settings, and this contains things that are shared across transmit and receive. We'll have the enable state machine. You can change it from FDD to TDD modes to pin control modes. the calibration modes. This is primarily for the transmit calibrations, but there are some receiver calibrations that you can control. And then we have some of the filters that you can load up into the device. Following that, going down a little bit, we have the receive chain. And here we can select the RF bandwidth, we can select the sample rates, the LOs of the receiver, and we can disable or enable some of the trackings. And then below that is the transmitter, where we can set that LO independently as well. The sample rate, if we change it for the transmitter, will change for the receiver. They have to be matched. It's just how the part works. And then at the bottom, we have our FPGA settings. And this is where the DDSs show up. And this is where you can control them and load up waveforms and generate signals from the boards.
What means
DDS? What is it? Which one? So,
on the right, on the top?
is it further up?
Yes.
So, baseband. Yeah, so baseband DC correction. And this,
That means you disable the filter?
so it disables the tracking. Yeah. So it's pardon?
When it is checked, it is disabled.
The tracking is disabled. So the baseband corrections, they're tracking on the receiver. They show up essentially as filters. They're not filters, but they appear that way. But you can simply turn the trackings off. You can't like disable essentially the tones that they generate inside. The diagram that I showed before, so this diagram of the 61 that's inside the tool itself, this is the simplified version of the 61. There are like 8 DACs and 5 ADCs inside the part that we don't show. And those are used for the tracking and for the calibrations of the part.
Relatively low speed ADCs.
Yeah. Okay. Now, I'm going to go back to the capture window here and select voltage 0 and voltage 1. Actually, I'm going to change this to a frequency domain plot first, and then select voltage 0, voltage 1. This is just I and Q of the first channel. And I'll hit play, and I'm just pulling back data. This is really useful for just like simple visualization, bring it into the lab, making sure the part's working. And then I'll match the LOs together so I can see what I'm transmitting. And you can see the LO from the transmitter. And then I'll simply enable a tone and add some amplitude to that. And you can see that on the right. So this is really useful for just like debugging, checking some performance of the device. And there are really useful features inside the plots. So you can enable peak markers and pull out some basic information from the tool. So are there any questions on IOScope? Yeah.
So you said that typically these are the models that came after the FM curves, and is there a model-based design for this one, or can we use the FM curves?
So the FM comms is just an FMC card with a 9361 on it.
Yeah.
So
For the system generator reference design.
yes.
Can we use the same that is provided for the FM curves?
Yeah. So the code generation HDL tools that we provide, you can use system generator, you can use HDL coder for them, or you can hand code Verilog. You can do the same for Pluto as well. I wouldn't like do a ton of FPGA development on Pluto just because they're very limited resources, but you can do a lot of things on it. Okay. Now we're going to move on to the lab next, and the lab will go into starting with I/O tools and IOScope. Please start with the first PDF called Intro to I/O and IOScope that you've downloaded from that website. If people need me to bring the link back up, I can do that on the first slide. If you do have questions, please let us know. Mahai Adrian and I will be around. Just raise your hand, and we'll help you out. Now, when you need to, so IOScope has been installed, IO tools have been installed in the VMs. If you need to launch IOScope, just type OSC in the terminal, and that will launch it. Okay. Does anyone need me to bring the URL back up for the labs?
Where are the support for the...
Pardon?
Where are the support for the exercise?
So when you go to this website, at the bottom there'll be a zip file. Yeah. So there'll be 2 PDFs inside that zip file. Yeah. And the PDF that you'll be going through is Intro to LibIO and IOScope. Please only do that one, and then in the second half, we'll go into the second lab, which is using GNURadio. But if you have any questions, if you can't connect to Pluto, please raise your hand, and we'll come around and check out your machine. Like, I can turn it back on. Do you mind if I leave it muted, or? Yeah. So do you mind if I put it on mute, or are you just gonna? Okay. Okay. You had a question?
No, if I put the loop back, the gains make.
Oh yeah.
It's a slow attack for transmitter,
Yep.
but for receiver with the attenuation, I leave it in 12.
What? No, so just like leave it 10 dB backed off, and then it won't. Oh yeah, sure.
Just for your first slide. So
Oh yeah.
device.
Yeah, sure. Somewhere. Yeah. Does that look good? Or is it? It's a little fuzzy. Is that good? Yes. All right. Good.
Was the preceding one, there was a flash.
Oh,
here.
yeah. Okay.
That's great.
Yeah. All right. How are we working?
The file is there. Where do you find the demo?
So it's in the application. It comes in the application itself.
Oh, okay. So, it's where here?
So it's in. Let's see. Where is it? It installs like user local bin.
Yeah, I think so.
Let's see.
No, you have to go to the file system, yeah? Another level.
Yeah.
USR. Local. Maybe bin or maybe share. Yeah, no, it's not bin. It's local share. OSC.
And then scroll all the way down to folders.
You know what? I'll check it out on my machine.
Where's?
So it should be in waveforms.
Yeah, but where's that folder?
Yeah,
Because like all that stuff gets installed. Yeah, so it's user.
local lib os
Oh, okay. Yeah, so it's if you go back to the local folder, just up one directory. Yeah, lib
lib
OSC.
waveforms. They are here. They are QPSK.
Yeah, no filter. Yep. Yes.
What is the sensibility of the input?
The sensitivity.
If I would like to see
I don't know. Yeah.
how big,
So like what do you mean by sensitivity?
if I have, I don't know, 1 microvolt, is it possible to see the signal, or I need to have 100 microvolt on my the sensitivity of the input?
Yeah. So usually like so that's usually yeah, it's so
For example, for the real spectrum analyzer, you have the sensibility is 130 dBm or something.
So you have to pull up the data sheet of the part to see the exact number. So I can show what that is if you're curious. So let's see. AD 361.
Well, it seems
Yeah.
also that you sell preamplifier for such compute.
It depends on what your frequency is of operation. Like we make like wideband amplifiers, but you're usually pretty high power.
Autorisé.
Oh, okay. Let's see. Is that yes? Yeah. Okay, yeah. So if you scroll down to, let's see. Because it would highly depend on the gain configuration of the part, what it would resolve to. Because the sensitivity usually for parts like this, it has to do with like a standard. So you'll take like LTE or Wi-Fi and tell you the receiver sensitivity in like that respect. But because it's not traditionally like used as an instrument.
It works.
What?
So he's trying to load the
Yeah.
QPSK file
Yep.
and says invalid data or something. But he invalid data format, which is weird. But
It's
he
an old
has a
version of IO. It's not
older
the
version
last
of,
one.
OSC.
It's,
How old is this? Well, as long as it's like within the last like 2 years, like it should be okay. Oh, is this like apt-get installed?
Huh?
So are you using apt to install it?
Yes, I have.
Like, did
I
you
have followed the.
did you build it from source?
Yeah. No, I built from source.
Okay,
I think so.
then it should be new.
Yeah, I never seen. I never tried also this, but
So if you try like one of the older files, so
no, the mat files is loading.
yeah.
So the mat files.
Oh, what language is your machine?
Language?
Yes, what language is it?
Why? Why are you asking?
So there was a bug so older versions of OSC, sometimes the data formats get corrupted for non-English versions of Ubuntu.
It's Spanish.
Yeah, that's probably why. So I think it was like German and Spanish were the ones that broke.
Yeah, that's what I was thinking, that the locale is messed up.
Yeah.
We have.
Look inside the file.
Yeah.
It doesn't change anything, but the locale is picked up by IOScope when
changing
you
the local
change the local, restart IOScope should work.
You but know better than me. Yeah, you fixed the bug. Yes.
Give some help to.
Okay. So, well, this is GNURadio, so this isn't part of the first lab.
Sorry, sorry, I was, yeah, we were on.
Yeah.
This one.
Yeah. So yeah, we'll be doing this later on, and we'll describe it. Yeah.
All right. Okay.
Yeah.
Yeah.
Well, yeah, but there should be some.
Yeah. Excuse me.
How do we lock properly to signal? It seems backgarden.
We'll talk about this a little bit, but like, there's no synchronization inside the transceiver, so you're just receiving the raw samples that are coming back, right?
Okay.
So you would need timing correction to deal with the smearing. If you go back to the scope and you increase the points, so you got to stop it, yeah, and just change this to like 4,000. Okay, so it'll look a little clearer.
Okay.
But essentially, it's timing error.
Okay.
So you're sampling in between points.
Is it possible to have this
Yeah, it is. So if you change the sample rate,
sample rate?
yeah. So just so the sampling rate here, just change it to like 10.
To 10?
Yeah. So this will change.
Okay.
Yeah. So what it does is it actually change the timing between the transmit and receive. So you're essentially sampling at a different position.
Okay. I understand. I have to find the sample rate which corresponds
Well,
to the input sample.
so it's more of like the. So if you put on a loopback cable, it's like the delay across this time. Yeah. So like the fractional offset, and what sample rate would be an integer of that value. Yep.
450, it keeps at 2450, is it correct? Or?
Yeah, so it's actually, so it's a multiple of this number. So if you have an integer multiple of that number, then, so this will keep going for a number of other zeros, or another of the digits, because it's 2.45 meg. So the number here, if it's an integer multiple of this, you'll get it nice like that. But if you increment it by like 1, then that's probably not an integer multiple of that number.
I was surprised that you have lost.
Yeah, so this will be unique for every Pluto.
Oh, okay.
Yeah, it's calibrated at
And the other
at
thing
factory.
that I don't have a nice.
It'll be different for everyone. So the radio has no synchronization, so your timing offset between the transmit and receive.
The slides were made with a different version of the tool. because I have the question because I don't have the same tab.
Yeah, so
that's
that was
okay.
actually changed like a month ago.
Okay.
So these
no
slides,
worries.
yeah, have been around for a long time. Yeah. Okay. So who has finished lab 1? Okay, we'll give you a few more minutes then. So when was this supposed to go till?
Oh, I don't know. I need to check.
Okay, because we didn't start until like 2. So. Oh yeah. Sorry. Do you know when this ends? Do you know what time it's supposed to stop?
normally 10 minutes.
In 10 minutes?
20, 25.
Okay, through 25? Okay.
10 minutes.
Okay, we're going to move on to the next section. If you have questions after, please come by and talk to me. If you have more questions about the labs or the device. But we're going to move on and just talk a little bit about GNURadio and some of the components inside of it and what some of the knobs actually mean. But just before we do that, so for those who got to the constellation that you saw in the lab, which might have been like 4 points or 8 points or 9 points or some weird combination of that. Does anyone know why that happens?
DC offsets?
So it's simpler than that.
Okay.
So we're transmitting on the same frequency, and we have a cable. So you expect the signal to be perfect that you're getting back, right? Well, the cable has delay, and the cable will unlikely be a fraction, or an integer delay. So we're basically sampling the data at the wrong position. And this is why you need a tool like GNURadio to do synchronization signal processing. The transceivers are essentially DACs, ADCs, and mixers. There's no timing correction, no frequency correction, all these things that are necessary for a real receiver. Now, just to kind of just go over where these things come from, which are not just unique to Pluto and some things that are unique to the device itself. So as I mentioned, you have that random delay that you're getting, which means that you're essentially sampling at the wrong position in time. And this just comes from going out into the analog domain, just through that cable or over the air. Now, you might have also seen that the constellation itself is rotated. And that actually comes from the fact that there are 2 PLLs that are used inside the transceiver for the mixers. So there's one that drives into the transmitter and one for the receiver. And these have a random phase relationship. They're frequency locked, but they have a random phase relationship. So that means
It's not possible to synchronize the phase comparators of both PLLs?
no, not internally. No. So you could use the external LOs to help with that, but there's a divider that's not shown in this diagram, and that will cause a random 180 phase shift. And that is different every time you reboot the part. Now, if we look at like a eye diagram, which is a very oversampled version of the signal that we're seeing. In this case, this is QPSK, where we're looking at just the I channel here. And QPSK, we're transmitting 1s and -1s on the I and Q channels. And the signal will transition between 1 and -1, or not. And depending on how we sample, that will change the signal that we see. So if the signal is sampled at a, say, idealish place, then you get a recoverable constellation that looks like this. We see our nice 4 points of QPSK. But as you shift off that constellation, or off that position to less ideal places, you get these smearing of symbols, because you're essentially getting combinations of symbols. And as you shift worse and worse and worse, you get things that are non-decodable. Right? And this is why we need receivers. This is why we need receive algorithms that fix this timing offset. Now, if you add frequency offset, what that will do is actually cause, so this is the constellation many of you have seen in the lab, like 8 points. It will be random for everyone. But if you add frequency offset, you'll actually see it rotate. This is a really kind of interesting way to see what's going on in your signal and your receiver. So if you're debugging your receiver and you see it rotating, you know you have frequency offset. If you see these smearing of symbols, that means you have timing offset. And we have ways to correct for this. Okay. So I know we're a little short on time, so I'm just going to skip ahead a little bit to the GNURadio pieces. Okay. So for those who don't know, the support for interfacing with Pluto or other I/O devices, other transceivers, is done through an out-of-tree module called GNURadio. And this provides access to essentially any I/O device that you want to use, and allows you to feed data directly into GNURadio or out of GNURadio. You can install it for Windows. There's a Mac build. There's Windows, actually a Windows build that we have a full executable if you want to install it on your Windows machine. That includes all the libraries and all of the blocks that you need to use it on your host machine. This requires libio, obviously, but it also requires a dependency called libad9361, and this is just kind of a specialized library that we use for blocks like Pluto and the FM comms boards that give you additional functionality on the filters and some of the clock settings. Inside GNURadio, you'll see a number of blocks. We have specific ones that are for the SDRs, FM comms, Pluto, as well as more generic blocks. So we have attribute blocks, which are for interfacing directly with attributes. These work on like tags, on messages, as well as we have some additional math blocks. Adrian showed these off yesterday with Scopy. So these are used inside of Scopy to do some math operations. And when you install GNURadio, you'll find these. You're like, what are these? What do they have to do with radios? And it's really just blocks that we use for other projects and are really useful for some general signal processing. Now, just to kind of open up the blocks for Pluto a little bit and to describe how they're used. So the first line is the second line beyond the block ID is the context. So that string that we were using in the lab, that IP 192.168.2.1 is the URI. This is the address that we use for the device. If you have the Pluto connected to your operating system, like I do on my machine, you could plug in the USB name, which would be USB : and then the actual ID from libUSB. This would be usually 3 digits long. Then we have LO frequency, which is kind of obvious, sample rate, RF bandwidth. RF bandwidth is the bandwidth of the front-end filter that's on Pluto, and that's on all the 61, 63, 64 devices. And then below that is the buffer size, which is the buffer that libIO creates, pulls data back and forth. We have this option called cyclic. What cyclic will do is, on the transmit side, is it will take the first buffer that's passed to it. So if you have a like a signal source block, like a sine wave generator, and connect that to Pluto, or the IO block for Pluto, it will take the first buffer that you're given, pass that to the FPGA, and constantly repeat. And then it will not accept any more samples. Okay. But this is super useful if you don't want to worry about like contention on USB and guaranteeing that you're not starving the transmitter. Yeah, it's super useful for debugging. It's yes. Yes. Correct.
So because the RF bandwidth is twice the low-pass bandwidth, that's the reason
Yes.
for the question. Okay.
Yeah. Yeah. So you want it. So generally, you'll oversample a little bit. So you'll set up the bandwidth, the RF bandwidth, to be a little bit smaller than, or your sample rate to be a little bit smaller than your RF bandwidth. Attenuation sets the attenuator on the Pluto. It will provide at most like 7 dBm, 2 dBm, depending on the configuration and the frequency that you're operating at. Filter is actually to provide filter files to the transceiver, which are useful for configuring the 128 type filters that are inside Pluto. If you select this auto true, it actually loads up some predefined filters that we use. And if you want to use Pluto below 2 megahertz, you have to load a filter. So if you set this auto filter to false and don't filter, you can't actually set sample rates below 2.084 megahertz. The driver will just error on you. And the receiver is just the kind of the opposite, as the same parameters, except you get the additional options for tracking. So you can enable quadrature tracking, RF tracking, and select the gain modes as well. And then it shares the filters. One thing to note is that so the filter, if you will, the filter files contain configuration for both transmit and receive. So if you load one up on here, it will overwrite this guy. It depends on what block is instantiated first. And the auto filters do the same. So they load up transmit and receive. And it will actually also change the RF bandwidth, because that's part of the filter itself. Okay. Now just talk about a little bit these stream blocks, which are the generic blocks that are part of GNURadio. And you can use these with Pluto or FM comms boards or other IO-based devices if you want to, just to get access to those buffers and send buffers. And they have a similar interface, except you directly fill in the device name, which when we were doing IO attribute -D, we are getting the driver names, and you simply fill them in here. So we have CF89361 LPC, fill that in there in the PHY, and then you can fill in the actual parameters. So we can set this RF bandwidth in this case, and you can build up your blocks this way, or change the parameters if you want to extend them to handle other use cases. A newer set of blocks are the IO attribute blocks, and these are designed to access different attributes directly. If you want to, say, change the LO on the fly, a good way to do that is through these IO attribute blocks. And they have messaging interfaces, because this operation doesn't really make sense as a stream. It's a very asynchronous operation. So if you want to set like any attribute of any device that's IO-based, you can do it through these blocks. And the source is kind of just the opposite of the sync blocks for IO attributes. You could read out, for example, here I'm reading out the high threshold value of the AGC. You can read out the RSSI attribute that's in Pluto, which is a relative measurement. It's not a dBm number, just a lot of people ask. But it's commonly used for RSSI pulling out that information and pulling out different IO attributes. So just to give you some perspective on how the blocks are built, everything is inherited from a IO device source block or sync block. In the case of the 61-based devices, that goes to an FM comms source or sync. and then Pluto actually inherits from that and just reduces the number of channels that you're using to 2. Yep.
If I want to use a very low sample rates,
Mhm.
do we have a built-in mechanism for undersampling?
So if you want to use Pluto at a low sample rate, you have to load up the filter to get the extra decimation. That will bring you down to 530 kilohertz. If you want to go below that, there is a filter that's available in the FPGA that you can use. And that gives you an additional decimate by 8. So that will bring you down to 65 kilohertz. And there's a special attribute you need to set. Yep, it's in Pluto today. Yeah, so if you look at the driver, the CF809361 LPC, the receiver driver, and you list the attributes there, you'll see one that says sample rates. And it will give you 2 options. One that's normal and then one that's decimated by 8. And you just set it to the decimate by 8, and you'll get the lower rate. So it's, since it's in the FPGA, it's a little bit separate than the standard driver, so you need to kind of add this additional piece to get access to it.
Is it a combination of CIC and a FIR filter or something like that? Or
Yeah, it's just I believe it's a CIC filter, yeah.
so the face is flat, right? Or the face is flat?
Yes, so I believe it's like 80 dB down.
Okay.
Yeah. Okay. Now, so the next lab we're going to go into, that will go into using GNURadio. That will show you how to go from the command line and then add attributes into a I/O device. So we'll build up essentially a Pluto block using the stream devices. And the device-specific blocks, they're built this way. We just kind of predefine the attributes for you. And what I really want you to get out of this is, so in the Pluto blocks, we provide kind of standard attributes for you to set. But there are over 200 you can set on the transceiver. And so Pluto, we don't want to scare people off with all these settings. And that's why we kind of limit the ones that you can set in the block itself. But if you want to extend the blocks, a great way, an easy way to do that is with the generic sync and source blocks. And the lab will show you how to actually create one for Pluto. Okay? So the lab is just a second PDF. And I know we're kind of short on time, so if there are any questions about the lab while you're going through it, please raise your hand. After the session, if you have any questions, please come by and ask me. Okay. But yeah, so the lab is self-guided like the first one. It's the second PDF, the Intro to GNURadio and IO. Oh, it's hot in here. We're a little over time.
Oh, good.
So how are we doing on
it would be good to finish in about 5 minutes. Is it okay?
Okay. So like the lab is just kind of like the end,
Okay.
and so it depends on how fast people can go through that.
Yeah, sure. So I think if we're going to leave them, I don't know how long it takes usually for the lab, but I mean, we're just postponing a little bit the end of the whole session, so if people don't mind So what might happen is that people might start leaving
Right.
for the next one if they have a train to catch or something.
Okay,
So,
okay.
I mean, it's really up to them to decide.
Okay. So are they going to come in here, or do you want me to swap?
That's what my colleague just got an HDMI to VGA.
Okay. Yeah,
adapter.
there's one hooked up there too. So. Yeah.
Okay, so we've got plenty of these.
Okay. Yeah. So we can just hop over.
So I think it's easier for the students to stay in the room.
Yes.
And for
Okay. Yeah, that's fine. That's fine.
also.
Right. Okay, we're about to start. Well, the title, you've already seen it. I start first to present myself. I'm Hervé Beuglen. I'm an associate professor at the University of Poitiers, which is in the west of France. I work also at the XLIM laboratory. So I would like to present you something that was hard for me when I started the tutorial. I'm an electronics guy, so I'm not really fond of computer science. So when you start with things like that, can be quite tough. Well, it's a question of time, in fact, to get accustomed to the system. And GNURadio is really powerful, but it's something also that's quite complex. I noticed that in the last group because I did about 1/3 of what I expected to do. So, well, perhaps you'll be faster than the others. I try not to make the same mistakes as I did with the others. Anyway, so let's start with what I would like to show you. So in fact, I'm going to talk about a Nordic semiconductor, which is some people already know them. They are from the north of Europe, and they are semiconductor manufacturers, and they're very well known in the IoT field because they've got chips that are really interesting that you find in a lot of products, especially in sports, keyboards, wireless keyboards, mice, drones, etc. So they've got a proprietary protocol, which we are going to see, and we are trying to decode and to replay it with GNURadio. So our goal is to build a transceiver, transmitter and receiver. So when you start with that, you say, oh, should I start from the beginning doing my own OT module? And most of the time, no, because when you think about something, you know that on the planet someone else has already think about the same and started already a certain work. And that was the case for this solution here. It's an American guy working as a specialist in the security. He does a lot of challenge in conference for hackers, and he's quite good. So he did an OT, built an OT module called GR Nordic, and we're going to start with this module, and we're going to change certain things in the module to adapt it for our needs. Because as you will see, it doesn't exactly work as it should, and even it's got bugs. So we'll try to go inside this to build our module to suit our needs. So that's the third part, and after that I finish with a conclusion. So what I noticed in the other group, it was obvious for me since Tanguy did that this morning. I thought that everybody was adding in his head the organization of an O3 module in GNURadio with the different directories and things like that. Apparently it's not the case for a lot of people, so I had to explain some things about that. Though, well, because some of you are probably geeks in GNURadio, some of us not. So if I go too far or too slow, don't hesitate to tell me. Okay? So for people who have already worked in embedded systems, you probably know this module. You find it on Chinese websites for less than €1. Something surprising, because when you try to build to buy the original chip from Nordic, it costs you €4 to €5. So how the Chinese are able to go down as that is simply because these are not original chips, they are fake. And in fact, there's someone that just dismantled the circuits and with a microscope had a look on what was inside. And the original one is manufactured with a 250 nanometer technology, whereas the Chinese one is with an oldest technology in 359 nanometers. And also, be careful when you buy these modules. They have not exactly the same performance than the original. If you expect to have a certain distance, communication distance, the Chinese ones are not good, and especially the antenna is just bad. But for something like between 5 to 10 meters, that's okay. So be careful about that. That's exactly this chip that we are going to mimic with GNURadio. So what do you find inside this chip? Well, it's already something that's quite complete. You've got the transmitter part with the power amplifier, a TX filter, and its GFSK modulation. Okay, and the same with the receiver with a low noise amplifier and the demodulation stages. And the baseband part is something really interesting because it deals with the packetizing side, and it's quite easy to use. You communicate with this chip using the SPI protocol, which you find on most microcontrollers. So this chip is quite well known and really used a lot for a lot of applications. So these are the main characteristics summarized. You can go up to 2 megabits per second for the data rate. The maximum output power is 0 dBm, okay? And the consumption is quite low because it's for embedded systems. And the sensitivity also is quite good. So if you don't add a power amplifier with a good antenna, you can have something that's about 95 dB of link budget, which is quite interesting. So the payload is limited to 32 bytes, okay? That can be a drawback in some applications. And the voltage, so the voltage range it goes up to 3.6 volts. If you want to have more details about this chip, you've got the link for the data sheet that you will find on the internet. So the protocol we are going to build here is, in fact, what they call the enhanced shock burst protocol. So it means that when you use this protocol with the chip, you've got a packet with these fields. So the first field is the preamble, which can be either OX55 or OXAA hexadecimal, depending on the address. If it starts with a 0 or a 1, and the address side field is can go up to 5 bytes. So a transmitter or a receiver has got an address, and this is sent with the packet. The packet control field is something they've added in the enhanced version. It gives you the payload length. 6 bits means that you can go from 0 to 31. Okay, so 32 bytes in maximum. The packet ID, that's a feature also. The transmitter can send several times the packet, up to 4 times in fact, and that's the packet ID, which is incremented from 0 to 3. Okay, and there's also a nice feature. You can have an auto acknowledge in one of the communication possibility, and this is the bit you set. If it's set, it means that you acknowledge. You expect the receiver to acknowledge the packet, so it sends a packet to say, okay, I've received the packet. Okay, that's on one bit. We are not going to use this here. Okay, the funny thing, also one of the reasons I wanted to go a bit more deeply inside the thing, is that you can have an NRF24LU1 plus, which is an NRF24L01 plus, just the one we have seen, plus an USB full speed chip, plus a microcontroller 8051. It means that in a USB mouse key, you've got this, and you can change the firmware and use this as a transmitter, as a packet sniffer, and can be quite interesting. So if you've got this kind of dongle with an old mouse that doesn't work, don't throw it away, keep it, because it can be a transceiver for the 2.4 gigahertz band, because it's got a mode where you can send a sign on the different channel, so that's quite interesting. It has to be a unified dongle. It's a special type. I say a bit more about that later on. Okay, so the NRF24 has been phased out by Nordic, and now it's replaced by the NRF52 series. They're still compatible with the old chip, but they do more things. They integrate a microcontroller. It's an ARM Cortex M4 in all these chips, and of course they can do Bluetooth. They can do NFC, ANT, ANT+, several other protocols, and it's not more expensive. They are really flexible. If you want to play with this, you can buy a development kit like this one. For 40 euros, you've got the development kit with the NRF52, and you've got the JTAG debugger already, a J-Link that you can use for overboard. And you get also 10 samples of the chip. So when you see the price of the chip, 10 samples would be more than 40 euros. So it's quite interesting. And there's a lot of documentation about that. If you want to look, they've also developed a lot of applications on smartphones to play with Bluetooth Low Energy. And it's really nice. Nordic hasn't given me any money for that, so it's not an advertisement. So where do we find an NRF chips? We talked about with Leo about that. You find them also in drones, like this one. So you can play, trying to decode the protocol with this drone. You find them in bike computers, in watches, in keyboards, mice, and in a lot of devices which need a wireless connection. So you find them in a lot of products. So that's why it's interesting to study them. So it's a well-known technology. I found quite a lot of resources about AX. The packet communication is also something interesting, and not something easy in GNURadio. That's also why I wanted to fiddle with this. So the goal of this tutorial, if you accept the mission, is to build a Nordic NX shock burst compliant transceiver with GNURadio. So I've got two boards fitted with an NRF24L01 plus that I will put in the room, so you will be able to see if your receiver is working or not. Okay. So for those interested, I'm quite fond of STM32, so it would work on an Arduino, but I've done the code for the STM32 and also the board for those who want to build the board. I will give everything, okay? So let's have a look on what's available for our system. So the question, do we have to start from nothing? Thanks God, no. But anyway, there are not so many up-to-date implementation. I found the one that we're gonna use now, and also an older one, which was for a Texas Instruments chip. It's quite old, 2014, so some of the blocks are not compatible with the new versions of GNURadio. But it's interesting to see how they build the thing, especially using messages. So the module we're gonna fiddle with is the one that's built by Bastille Research, called GR Nordic. It uses the GNURadio message passing interface, okay, not streams. It has been designed to identify vulnerabilities of wireless keyboards and mice, and it's been presented, well, what they call mouse jack. It has been presented in DEF CON 24. It's a hacking convention by Mark Newlin from Bastille Network. He's a specialist of security, working normally also with DARPA in the USA. So in fact, he identified quite a few vulnerabilities in wireless keyboards and mice, and he started a work on that. And thanks to him, the Logitech and Microsoft changed their system because of the vulnerabilities they showed. So that was quite interesting. It's not only hacking, it's also helped to improve the security of the system. So especially if you say that to someone who wants to hack something, he starts with this type of message. Okay, I start tomorrow. Because since the displacement of a mouse would not give any useful information to a hacker, the mouse reports are not encrypted. That was in 2009. It's no longer the case now, but see. So classically, with a wireless, it's quite handy, wireless mouse. So all the movement and the clicks are sent by radio to the dongle. Same for the keyboard. So in fact, thanks to the USB interface, you get the packets, and the PC treats everything, so that you've got everything on your screen. And what you can do as an attacker, you can talk to a dongle, but also more interesting, you can eavesdrop on an unencrypted keyboard and get the passwords. Okay, so quite interesting. If you want to have more details about that, you've got the link of his presentation to DEF CON, and it's really interesting because it details everything. Okay, it's time to work. So first thing you'll have to do is to get the GR Nordic 003 module, just by the command git clone. Should work with no problem. So if you are lazy, like me, and you don't want to tap everything, just open the navigator, go to Google, you tap GR Nordic. I know the navigator on the virtual machine is Dilo. Dilo. Yes, it's possible. It's open. Je lui ai demandé. Il m'a dit que c'était bon et on a testé là, ça marche. So either you tap it like that. Alors, so I suppose that everybody knows what a Git server is. Yes?
Yes,
Because it wasn't so obvious in the other group for some people. After that, you know also how to build. Okay, that's fine.
just a small problem here. Logging in, can you help us log in? Or somebody else?
To log in.
Yeah, I'm not sure what that we accidentally put it.
The problem is that the key is on the height of my knee.
Oh.
So I hit it.
Jean-
Somebody from
Tanguy, tu sais, les mots de passe de Windows, tu les as ou pas? Parce qu'ils peuvent pas se loguer en Windows. Des bécanes en Windows. Did you have to enter a password to log in on the Windows session? No? It was open already? Parce que someone has a problem with the password. Well, Dilo is an old-fashioned navigator. No, I prefer that you don't do that. I don't know it. Well, so if someone has already tested the GNURadio on Windows, you shouldn't do that. Well, I tested it. It works on Windows 10 because there's a group that, in fact, builds the system for Windows, and it works pretty well on Windows 10. I've got a PC with Windows 7, and it doesn't work on Windows 7. I don't know why. So Windows 10, it works pretty well. But of course, when you cannot add easily an out-of-tree module, because of course you have to install all the build system inside the bloody Windows, and just don't do that. Try to work with Linux. So just one thing, if you know that, that's important. Everybody knows that's what means -J2. Just a simple example, when you install GNURadio from source and you just don't use this option, you just type make on a powerful PC, it can take more than 2 hours to build all the system. If you've got a Core i7, you've got 8 threads on the processor, and if you type -J8, it takes only 15 minutes. Because make has been parallelized on the new Linux distributions. So if you've got a processor with several cores, don't forget this option, because in terms of time, it's interesting. Yes?
This morning we have set up some environment variables to put the modules that you not local directory. Will it be valid also for this?
No, in fact, what I intend to do is, with the git clone, you'll have, in fact, the directory gr-nordic in the virtual machine.
So what I think is that you can use here the cmake command that we have in order to install it on your local directory to make no change. You just don't do the sudo.
We don't do the sudo.
If you do cmake dot, it will be installed in /usr/machin. So you have to do sudo make install.
Okay.
So if you do the -d prefix install so on, you don't have to do the sudo here.
It's not the config people is doing inside the sudo and the command is not containing the library.
So there were two threads, two cores on the virtual machines, but we tried for some machine it doesn't work. So if you've got an error when you type -J2, just get rid of the J2 and just type make, and it's going to work. So doing these commands means that you're going to have this out of 3 module installed on your system, and normally you will see that some blocks will appear in GNURadio Companion. We'll check that. Alors, just a question. Ouais, tu le refaisais installer localement, c'est-à-dire tu le faisais pas? Ouais.
Tu mets -D, -grand.
Ah oui, mais je l'ai vu la commande en fait. Parce que moi l'idée c'était que ça soit disponible sur le système si tu veux. Je l'utilise après.
C'est comme ça, mais c'est vrai qu'après tu es obligé de faire des sudos partout.
Ben, je le fais juste pour le make install en fait quoi. Mais c'est vrai qu'il faut que j'y pense à ça. D'accord. Ben, on va tester quoi. Okay, everybody's ready with these commands?
No, well, I will fix it,
Yeah. Essaye de les mettre dans GRC. So if you've already finished that, try to look, you open GRC, GNURadio Companion, and have a look to find the blocks. There should be 2 new blocks. Yes?
A Git, it's a repository where we can find all the files necessary for...
A Git server is in fact a machine that you find on the internet, and this server has got several functionalities when you develop code. For example, you want to build your OOT module for GNURadio. Okay, it's your module. If you want to follow the modifications of your code by date, you can use Git. Git is very good for that. For example, you put all your code. 1 month later, you want to change something. You change, it doesn't work, so you can go back to the first version. It includes a versioning system as well. And the other advantage of Git is that you can have several people working on the same server. Well, normally you give them the right to do it because you don't want everybody to modify your code, but that's the possibility of the Git system.
Okay, so by doing Git clone...
It means you take a copy that's on the website, and it's going to be put on your local machine.
Okay, so it works on all the things that are on GitHub?
Yes, yes. Yes, if the person that shares the code, yeah, you can have several possibilities for GNURadio, for example. Most of the people who develop OOT modules, they use a GitHub. Yeah.
And it could be on one file, like a full repository of.
Can be one file or something more complex. Yeah. With a lot of directories. As you will see, we will have a look on what we are going to get here. You will see that we'll have quite a lot of directory on your machine. Yes? Exactly. Yeah, try to put exactly.
Yeah.
It's normal. Okay, so for those who have tried to get the blocks and to put them into GRC, it doesn't work. Okay? It's normal because these blocks haven't been written by the authors, so we'll have to do it. It's a pity. The XML files.
Okay, they are missing the...
Yes. Well, you've got the template, but nothing has been done for that. Well, it will take a certain time, but anyway, I'll give you the codes. So, okay. Do you know how to, starting from a new block, reading the I/O signatures, how to adapt the XML file according to that? How do you make the relation between the GRC blocks written in XML and the C++ or the Python written blocks. Do you know how to do that? Okay, so we'll have to do that. So if you look here, what you should do first, well, because that was a problem with the other group, so as I remember the problem, when you did the command git clone, you got a lot of new files on your PC, and the architecture is always the same for an out of three module in GNURadio. I suppose that you know these subdirectories. The first one is the lib, where you find all the C++ blocks, okay, include all the headers related to these blocks, okay. GRC is the directory where you find the XML files that GNURadio companion will use to draw the blocks with the input outputs. What else? If you write blocks in Python, you will have in this directory Python files, okay? And something Tanguy already talked about that this morning, so I won't go further. Everybody knows what Swig is. Swig is a wrapper which allows Python to talk with C++ blocks. Okay, so that's an important directory. You will find, of course, the build directory where you build everything with CMake, and also the CMake directory where you've got all the definition files that CMake uses for the compilation of the module. Okay, so let's have a look now in the lib directory, and in the lib directory you will find C++ blocks, okay, and there's one that we would like to study, because when you start with an OT module coming from the web, it's always interesting to see how it has been written, and especially the inputs and the outputs of the block, especially since you've got to build your GRC blocks, okay? So let's have a look on this one. This is the Nordic TX, okay, that's the transmitter. So what about the input and the output? Do you notice something particular for this block? 0, 0, 0. Yeah, 0, 0, 0 for the input. So suppose he hasn't got any input. It's not true, because in fact, when you use the message passing interface of GNURadio, you find the input here, okay? But it works independently of the rest, okay? So it doesn't go in the IO signature for the input, okay? Can be the same for the output. But of course, for the output, we've got something defined here. It can have multiple outputs because I've got a variable called channel count. So apparently this system is able to send packets on different wireless channels. Okay? So our GRC block should be configurable. So if we want to choose 2 outputs, it should work normally. Okay? We'll see how we write that. So just a little thing with, okay. For the message passing interface, it uses PMTs, so a bit strange things, but well, something quite interesting. I'll talk a bit more about that afterwards. So in fact, when you've got a message as an input, you've got to have a function which is called a message handler in your code. So this message handler, every time a message comes in, its role is just to treat this message. Okay. So if you look further in the code, you will find that, because the you have to do a bind, and the function is called Nordic tap message handler in that case. Okay. So with the I/O signatures, we are able to write the XML code for the GRC files. Okay. I won't ask you to do it. I'll give you the code. And the other one, just to see the RX. So the RX, we've got a bit more things. So it's just the reverse of the other concerning the I/O signatures. We've got something which is a stream in input, but output we haven't got anything. It's in fact again a message port that's for the output. Okay, so we'll have to deal with, on one side, streams, and the other side with messages. Okay, we'll try to get the files if Jean-Michel has done the work. He told me that it was okay. No. The name I gave, we'll just check that. Friedt. Consulte le bordel. Okay, so there was the previous. So you can do, in fact, what I ask you to do, it will take more time than 2 hours. So I've put all the validations, all the modifications here. You can get it. So normally Jean-Michel has uploaded the new version. So you just have to type wget on gmfried.org, and be careful. Try with not with this name, but with the new one. So the new one should be, okay, validation step Nordic. I think it's S, yep. So wget should work, hopefully. So normally it's validation steps Nordic. I was just checking because that's the new version. The old version, there was a missing file. That's why we uploaded it again. So wget, it's just here. No. But normally the last name is this one. If it doesn't work, okay. So the dots is not yet on the. So take the old one for the moment, because the new one apparently is not yet on the site. Yeah, Steps Nordic. Yes, that's the name. Cool. Et l'autre, il était, il n'y a pas de problème, on l'a déjà.
Ça commence par T.
Ça commence par T, T majuscule, tutoriel.
T majuscule. Ouais. Ah, les majuscules sont en devant. Ouais. Celui-là y est.
Alors regarde voir.
Ah voilà, validation steps.
L'ancien y est.
Nordic.
And the new one is already on.
Validations.
Validations, sorry. There's a missing S, so the new one is already on the site. Okay. Yep, validations. Thank you, Tanguy. So take this one. That's the last one. Yep. It's okay for everybody? À boire, à boire. T'es avec la chaleur qu'il fait là. Ah, c'est pas étonnant, oui. Ouais,
il paraît que c'est bon de boire chaud quand il fait chaud.
Oui, c'est ce que j'avais entendu aussi.
Ça force ça permet de rafraîchir.
C'est bon?
L'ancien, oui.
Non mais le nouveau ici, il manque un S.
Non, en fait l'autre il avait tutoriel.
Oui, mais justement le nouveau il n'a pas tutoriel, mais c'est validation au pluriel. Donc, ouais, et nordique, normalement c'est ça. Ouais, je pense que c'est. Ouais, c'est un underscore, c'est pas. Oui, sorry. It's an underscore, not a dot. Ça marche pas? Doesn't work? You got it?
Ça marche.
Ouais, ça marche. Hein, bah, normalement, c'est bon. Et puis, bien, validation au pluriel, c'est bon. Ouais. Oui. Be careful. Linux is case sensitive. So, capital V, capital S, capital N. Yes, that's right. So every time we do something, it's V1, V2. Okay. So you've got the things that are okay. Okay. So normally you should be able to modify the XML files to so that they work in GRC. But I gave you the solution. You've got this in the V1 subdirectory in the archive. Okay. So just remember that for the public constructor, the make function you find in the C++, you have to find it here. And when you've got parameters like here, we've got a variable. It becomes a parameter here, okay, of type int with a default value which is 1, okay. And funny thing, the number of ports at the output can change thanks to the value of this variable. Okay, so that's the Nordic TX block. So now, what do you have to do? You take the files you find in the V1 subdirectory, you copy them in the GRC subdirectory of your module. Okay, so you replace the old one by the new ones. What do you have to do after that? So, yep, you have to go for a build again, okay, so that it's recognized by GRC. Okay, don't forget that every time you've got a modification like that, you go into the build directory again, and you start a new build. Make. Voilà. Ah, ça c'est CMake, c'est pas la même chose. Non, make c'est juste la compilation. So what's the difference between make and CMake? Because it just asked the question. Doesn't do exactly the same. No. Exactly. CMake is a system that builds all the make files, all the files you need to compile something. Okay, and the make command does the compilation and the link to have an executable at the end. Okay? So CMake just looks, apart from creating the make files you need for make, it looks also on your system if you've got all the dependencies you need to build a module. And so if you have done CMake already and you've got everything on your system, you don't have to type CMake again. Okay? After that, it's just make. Ah ben, normalement, on va retrouver les blocs maintenant.
Bah, oui, je les ai, mais du coup, avant, on les avait déjà aussi, non?
Non, avant, on les avait. Ah oui, mais là, c'est pas bon. Et maintenant, il faut mettre. Donc, le problème, c'est qu'il faut mettre à jour. Donc, il y a ça.
Ça doit fatiguer. Je l'avais fait, ça, pourtant. Enfin, je l'ai coupé, puis je l'ai remis.
Oui, ben normalement, ça devrait marcher. C'est à condition d'avoir fait un build et un sudo make install. Faut refaire toutes les commandes. So, normally, if you've done things properly, you should have the same thing as me. In my GRC, so oops. You have to copy the 2 XML files. Qu'est-ce qu'il me fait là maintenant? Putain. Super. So you have to copy them in the GRC. Okay for everybody? No, normally you see the blocks and everything seems to be fine. Okay? Yes? Yeah, just 2 blocks at the moment, yeah.
Là, je le vois bien, là, mon fichier.
Ouais.
Il est ici. Donc là, il est là. Et du coup, j'avais fait un unzip de ça.
C'est ça ce qu'il faut faire. Ouais.
Mais enfin, je sais pas, maintenant, j'ai pas de fichier dedans.
Et normalement, si on fait le unzip, il crée le répertoire. Alors là, si on fait un... donc il est là le truc, hein.
Oui.
Donc unzip, c'est un clavier. Oui, si je le fais à l'américaine, unzip. Et donc... oui, donc là, normalement, il va le créer... alors, on va faire yes to all. Ouais, pour all. A majuscule peut-être. Ok, donc là il les a collés, il les a mis où? Dans Steps, donc il y a un répertoire qui s'appelle Steps. Voilà. Donc en fait maintenant les V1 c'est ça, on les copie. Copier. Voilà. Et on va les mettre dans justement un cran plus haut dans GRC, encore un cran. Donc là dans le répertoire GRC, donc on écrase les anciens. D'accord? Donc là, on fait overwrite. Voilà. Et donc là, on a les nouveaux. À partir de là, GRC va être capable de les revoir.
Ok. Donc là, quand on met à jour...
Voilà, normalement, on va les avoir. Alors, pour l'instant, c'est dans nos modules specified. Je vais expliquer pourquoi il y a ce truc-là. Donc, nordique, voilà. Non, c'est encore les anciennes versions. Donc, ce qu'il faut faire, bah oui, parce que là, on a juste les copier. Donc, maintenant, il faut faire un build. Hein. Ça, donc là, si vous faites le build et puis vous refaites votre truc, ça sera bon. Vous les aurez, quoi.
Ok, donc je retourne dans build.
Il faut retourner dans build, oui. Voilà, build, ensuite make et sudo make install. Ouais, ouais.
L'étape avec le steps, j'ai pas compris.
Oh, okay. So what's inside when you unzip this file, you will have a steps directory created, and inside this directory, you have got all the solutions of the thing you have to do during this session. So when it's V1, you've got already the correct files that you can copy, so you don't have to do the job, in fact. Okay? So for example, when on my slides you see V1, it means that in the subdirectory V1, you've got this file already. So you just have to copy it inside the GRC. Yes, of course. The slides are already, you can get them if you want to have them here. So see, if you want the slides, to look at the slides at the same time, yeah, they are on my website. Okay, so that's what we have to do to make these blocks available to GRC. So you just copy the two files you've got in the V1 subdirectory into the GRC directory. When you've done that, you go to the build directory and you start again a make and a sudo make install. And then you refresh into GNURadio companion and you will see the updated blocks, and you should see the blocks, the working blocks. Okay? Yep. Okay for everybody, yeah? No, it's clear for everyone? Okay. So now what we want to do is to try with the code that's already existing. You've got a directory called examples, so it could be nice to try with this. I've got two STM32 with the modules, so I'll put one here and the other on the other side, so you can check your receiver with this. So how is the packet, the ESB packet constructed? My STM32 sends a packet every half a second, okay? So the payload is supposedly the room temperature, but you'll see that's to refresh you. It will send you 20 degrees. It was just to test the code so that the temperature wasn't changing, because I wanted to see exactly what I get inside the packet. So, but it's not a problem because I've got temperature sensors on the boards anyway. So the address is OX55 5 times, okay? The payload is 8 bytes. In the payload, you've got 4 spaces plus the temperature in the form xx.x. Okay, so in our case, it's going to be 20.0. The CRC is going to be on 2 bytes. That's something you can configure on the NRF24. The data rate is going to be 2 megabits per second. And the RF channel I use is the channel 85 because I want to be outside the Wi-Fi band, because when you fiddle with these modules, and you've got Wi-Fi, it's going to be a trouble. So up to 2.8, yeah, it's okay. Wi-Fi is just under. So that's why I chose this channel. So okay, let's go with the transmitters. Well, you can put one here. You'll be the
Good.
Yeah, okay. Yeah.
So you just need to
Your new
connect.
antenna.
So normally it should work pretty well near your Pluto. So what we want to check now is the receiver, and there's a nice example in the example directory called Nordic receiver. So open this file and don't be as lazy as they were in the other group, because if you tap on only Nordic receiver and you forget the arguments, it's going to look at channel 4 by default. So when you open a Python file you don't know, look at the code, and especially the input arguments. And that's normally at the end of the file. So I'm going to open the file to show you. I've got more examples because I did some things myself also. So it's the one is Nordic receiver. So first thing that you'll have as a problem, they say that this OOT, so exactly the term they've used, it is supposedly SDR agnostic. What does it mean? It means that they use the Osmo SDR library, which works with USRPs and a lot of other devices like RF and things like that, but not with the add-on Pluto. Yeah. So what we have to do is to change a line into this code, to this file, so that it works with our Pluto. Okay? So you have to modify Nordic underscore receiver dot py, and add a line so that your Pluto is recognized. So you have to comment all the things that deal with Osmo as the SDR, okay, and add a line to add a Pluto source with another problem. On my machine, I don't have to precise the IP address, but you will have to precise the IP address and put 192. Okay. You've already the solution in the V2 directory normally. Okay. So if you are lazy, you can directly go to the modifications. It's in the subdirectory V2. Okay. Don't forget, change this line, and also to add the line to import the IIO library from analog devices. Okay. Another thing I've noticed with the other group is that people are not, some of them are not really accustomed to our Python file for GNURadio is built. You've got a lot of information about what's inside the file and what it does. Especially when you look at the connect keyword, okay? You see that, for example, here I start with a Pluto source that I connect to the input of a LPF low-pass filter. This low-pass filter, the output of the low-pass filter, is connected to the input of the GFSCAD demode block, and the GFSCAD demode block goes to the RX. Okay?
Can we have access to this PDF? So
because you are...
It's here.
Ah, okay.
It's on my website. I said that before. Sorry.
Okay,
So if you want to have the...
so we can trace back.
Exactly. So you can have it on your screens, and it's going to be easier.
Yeah.
You are right. Okay. Okay. So normally, what it should do, finger crossed. And don't forget to read the arguments at the end of the file. Yeah, so for the bitstream, mais en fait tu peux le commenter parce qu'il n'en a pas besoin. Oui. He's not happy with a bitstream module missing, but you can comment it because we don't use it. But otherwise it's sudo, enfin c'est un SU apt-get. Léo l'a trouvé, ça doit être Python mais on n'en a pas besoin. Where's my Pluto? So normally the antennas of you've got for the Plutos, they work pretty well. They are matched to 900 megahertz, and not optimum for 2.4 gigs, but anyway, it will work. Justement, c'est ce que je vais faire. Je vais te montrer.
Ah oui, c'est-à-dire que ça va imprimer des choses s'il y a des choses qui arrivent.
Exactement.
Donc c'est normal qu'il n'y ait rien qui arrive pour le moment.
Bah, si tu n'as pas de STM32 à proximité, ils l'ont pas, je ne sais pas s'ils l'ont branché. Moi j'en ai un là maintenant qui émet, donc tu devrais avoir quelque chose. Alors, et il faut surtout mettre un argument, il faut mettre le canal 85, parce que sinon par défaut c'est canal 4. Hein. C'est ça, c'est une bonne idée. 85. So, as you can see, it works. You see the sequence changing. What's that? Is the PC? Is your PC? Is your PC, in fact?
Sorry, that's just my Adobe. What kind of plugin is this? I was just trying to copy some text. Sorry for that.
Pardon? Le moins channel 85. Yep. Si, of course. That's because you're lazy, you don't want to go and read the... Non, d'accord. Bah c'est peut-être un truc à essayer, ouais. So channel 85, so for those who want to test, I can bring the board nearer to your Pluto. Can put one here, for example. Bon, j'ai le droit de vous brouiller. 2 Go 4, c'est moins que le micro-ondes. Hein, quand même.
Le source est dans le V2, le source corrigé.
Ouais, dans le V2, ouais.
Donc on va rien faire, on va juste
Bah,
faire
si vous êtes super rapide, vous pouvez le faire. Mais j'ai vu que, voilà, c'est... Yep.
il manque un argument.
Ah, bah je viens.
Le nordique tap out,
Ah ben pour l'instant, il n'existe pas. Hein. So what it's trying to do is to bring everything into GRC, but well, yeah, the Nordic Tap printer, it works in the Python code. There's a function for that, and what we want to do, that's the next thing we want to do, is to add this block and make it available to GRC. Because of course, well, if you like playing with Python, it's cool, but in GRC you've got a lot of interesting blocks to look at the signals and things like that, so it's quite nice to have everything into GRC. But already we've checked that it works on this channel with the receiver they've built in the example. So you said it didn't work on the website for the PDF? Okay, so I've made a mistake probably with the address.
It works, its capitalization is important.
Oh yeah, don't forget that it's the same as with Linux. The capital is the case sensitive. It's case sensitive also on the website, so that's normal. In fact, okay. Okay. Yep. Si, il y en a une. There's one that's missing.
It's bit array.
Yeah. So can you open the? Yeah.
Ah, il faut la commander.
Ouais.
Okay,
Mais on peut l'installer, c'est en faisant sudo apt-get install python -bitstream, on peut l'installer, mais bon.
Mais
on a
sur
pas
la
besoin.
commande, c'est
On s'en
bon.
sert pas.
Ah, il n'y a pas de souci.
Oui, c'est pas mal. Oui, non, c'est pas mal, hein, franchement. Okay, so you've seen the receiver works. Okay, everybody? With V2? So now we've integrated our Pluto. We've checked the receiver. It works. Okay. An important thing to know is how do you demodulate the signal sent by the NRF? Is by looking what they do here in this Python file. Of course, you need your Pluto low-pass filter just to limit the bandwidth, so to increase the signal-to-noise ratio. Okay. Then you do an FSK demodulation. Okay, you've got a block for that in GNURadio. And finally, you go into your block called Nordic RX, and that's the result we had in the terminal. Okay, so that's the blocks we will need in GNURadio Companion. Okay. So there's one missing block. Is this one? See? Because the RX has got a message output port, and apparently we need something called Nordic Tap printer. Where is this Nordic Tap printer? So not far from the truth. In fact, it's in the file Nordic receiver. It's a function they've done. Okay, so you see class Nordic Tap printer. Okay, so it's already implemented here. The trouble with that is that, again, the mic, it's not available in GRC and in other blocks. It's a local function. That's not nice. I would like to take this function, make a block, and this block bring it to GRC. that's next job. Okay, so it's quite easy. I'll show the procedure, and after that, either you code or you get the V4, I think. Okay, so the idea, everybody is okay with this? I need this block so that I can do the same in GRC. Okay, so the code is quite nice. It's already a sync block. So what I can do is simply go into the Python directory, okay, of the GR Nordic module, and create a new function called Nordic blocks. And inside this Nordic blocks.py, I'll put the code of the Nordic tab printer. Okay? But I've got to change a few files so that the build system knows what I have done. Okay? So in fact, I will have to change the cmakelist.txt, okay, this one. I will have to add Nordic blocks.py, okay, it's not finished. I've got to change another file, which is the _init_.py. Don't forget this one, it's important. And here you have to add from Nordic blocks, which is the name of our Python file, you have to do an import of Nordic tab printer. Well, I've already done the Nordic tab transmitter because that's the next step. I put the two blocks inside the file. Okay, so these three files, the first file, Nordic blocks, has to be created. You put the function in it, which is also a block, in fact. Then you modify the cmakelist.txt, and then this one as well, and it's not finished. You'll have to create an XML file so that the block can be recognized by GRC. And normally you've got everything in V4, I think. No, it's V3 probably. Yep, V3, that's right. Have a look, but normally it should be corrected. The XML file, there was a line that caused the problem. It should be okay now. I just open it. So in fact, either you modify the files I was talking about, or you take everything that's in V4 and you copy 3 of these files into the Python directory, and the 4th one, the GRC one, in the GRC directory. Okay? So to summarize, in V4 you've got 4 files. Okay? So 3 of these files have to go into Python. Okay? Python directory, so it's Nordic_block. That's the first one. The init has to be changed. Okay? And the cmakelist as well has to be changed. The 4th file has to go into the GRC directory, okay? And it's called Nordic_tab_printer.xml. Okay? And with that, you've got everything. Yep.
You put only the function
No.
Nordic?
No, I take everything, all the imports as well.
the import, but you don't take the top blocks. neither
No,
the
no, no,
main.
no, no, exactly. No, just the imports and the function that deals only with the blocks.
Okay,
Yeah.
and I'm not sure where from. So I'm in the init.p.
Ok.
Je fais. J'ai pas très bien compris s'il faut mettre la from.
Ah
nordique.
oui. Ok. Ouais. Mais oui, mais justement, mais en fait, le init, parce que ça, tu te fais avoir quand. Ouais, c'est ça. Non. Et il faut modifier le. Voilà, c'est celui que j'avais oublié, c'est le make list du GRC. Merci de le rappeler, je l'ai pas noté, celui-là, je l'ai zappé. Donc, ouais, alors Tanguy, ici, dans le init, c'est à cet endroit-là, puisqu'on n'avait rien qui était dedans, donc forcément on part de 0. En fait, il faut faire. Il faut écrire ça. Et là, tu mets le nom de tes fonctions, enfin de tes blocs que tu rajoutes, en fait. Yep, c'est ça. Le CMake list, c'est pareil. Donc, il faut que tu le modifies aussi. Bah, je me suis servi d'un truc existant, donc j'étais obligé de mettre les... And I forget a last thing to change also. You've also to change the CMake list in the GRC directory. So good. And normally everything should be fine. just this file, in fact. Just this line. I've added just this line. Yep. It should be a new block in the GRC. So I know what you've forgotten. In the GRC, if you can go in the GRC directories. No. Wait, yeah, here. Exactly. So you have to modify the CMake list.
Modify.
And add the new block. Otherwise, okay? So don't forget, in the CMake list that's in the GRC directory, modify it to add the new block. Otherwise, GRC won't see the block. Okay?
J'essaie de faire tourner votre solution.
Oui.
Donc Python, step 2, Nordic, Receiver,
Ça roule.
channel. Et il me donne device not found.
Oui, la Pluto. Alors ce qu'il faut faire en fait...
Non, mais la Pluto elle est bonne. Hein.
Oui, mais la Pluto elle est bonne, mais le problème c'est qu'il faut rajouter l'adresse. Donc il faut éditer le fichier. Parce qu'en fait, sur ma version, j'ai pas besoin de rajouter l'adresse IP. Si on la rajoute pas là sur le truc... donc faut... Guinea, alors faut utiliser Guinea. Hein.
Bah, je l'ai ici en fait.
Ouais, bah voilà. Donc,
et il est où?
Donc il faut faire open, on va le chercher.
Il est là.
Ah ben, il y est déjà, oui, ok. Donc en fait, il faut descendre. Tac. Et là, entre les guillemets, il faut mettre 192, 168.
Je me doutais bien que c'était du
Ça, c'est parce qu'on est dans une machine virtuelle et puis que, voilà. Voilà. Donc normalement, avec ça, ça doit le faire. Oui.
Mais là, du coup, j'ai modifié dans CMake list, dans le répertoire Python.
Yep.
Ensuite, il faut que j'aille dans GRC.
Exact.
Dans celui-là, et là, je rajoute...
Le nom du nouveau bloc.
Donc c'est Nordic...
Nordic Tap. Nordic Tap en un mot. Underscore printer. Et ça doit commencer par Nordic d'abord. Hein. C'est toujours Nordic underscore, c'est toujours le nom du module d'abord. .xml. Donc devant, pas oublier de mettre Nordic underscore.
Nordic underscore Nordic Tap.
Voilà, c'est ça.
Comme ça?
Ouais. Après, bien sûr, il faut nouveau tout compiler.
Ok, parce que du coup, il y avait juste dans Steps, il fallait juste prendre le Nordic block celui-là.
Oui, il fallait tout prendre. Hein. Si vous ne vouliez pas vous embêter, il suffit.
C'est pas grave, si j'ai laissé les autres, j'ai juste pris Nordic block.
Ouais, ça c'est bon. Ouais.
Et puis du coup, dans le V4, il fallait juste prendre celui-là et le mettre dans le GRC.
Bah ça c'est le GRC, le nouveau. Ouais. On a deux, trois petites choses à rajouter encore, on va voir, mais c'est pour la suite. Ouais. Mais déjà testez ça pour voir si vous avez bien votre Nordic Tap Printer qui apparaît.
Quand je fais Nordic Receiver Channel, j'ai un ce genre d'erreur?
Module as no attribute Nordic RX. Ouais, bah, il trouve pas le bloc. Il trouve pas le bloc. Donc les blocs apparemment sont pas existants. Ah, alors faudrait aller regarder dans GRC.
Ah, c'est pas un point.
Ouais. Donc, faudrait éditer le fichier donc avec GNI. Donc on va faire GNI CMake. On va se débrouiller tout seul, voilà. Bah, pourtant ils y sont. Donc, parce que là ils trouvent pas le bloc en fait, c'est ça le problème. Et ça c'est plutôt inquiétant. Ou alors il y a une erreur de syntaxe à cet endroit-là, c'est ce qu'il faut regarder. Parce que si vous avez pris mes fichiers.
Ben ouais, mais CMake il n'était pas dans le GR. Dans le V1, dans le V2 il y était?
Ouais.
Ah, je l'ai pas pris alors, je pense.
Ouais, bah, c'est peut-être ça en fait.
Ah, okay.
Donc, ouais. Ok. You've got your blocks. Où tu le prends, il est dedans, je l'ai mis. Dans la solution, dans le V4, ouais. Ouais, parce qu'après c'est. Yep. Ah, okay, I know.
Yeah, like we have the CMake list.txt here.
Did you modify the CMake?
We have the GRC, CMake list.txt. We have the Nordic blocks.py in there.
Okay, and there's another CMake list.txt which is in the GRC.
Yeah, I can show you. Yeah.
Okay.
GRC. So there's a CMake list.txt here, and the GRC directory is here.
Can you open it?
This one which you did see there.
No, it's not the right one.
And the one. Okay. Now we.
No, in the GRC,
yes.
It should be. I'll show you. It should be this one. The one you've copied. Okay. It should be in the Python directory.
Sorry, we'll check out.
Yeah, you inverted the. That's the reason. Okay, you've got the blocks. So you're ready to build your flow graph to have a full receiver, GFSK receiver in GNURadio Companion. And this is going to be something like that. So at the end, if I do the things properly, I should have my GRC model, which looks like that. So my Pluto. I've added something called a power squelch because, well, I want to decode a packet only when the power at the input is above a certain level. But that's normally what is done inside a real chip. Well, you have to try with the threshold values because it's not well documented. Well, you have to fiddle a little bit with that, but it works quite well. After that, you've got a low-pass filter, okay, again to limit the reception bandwidth. You can take the ear block from the library if you don't want to see what this GFSK demode block does, but it's interesting to go to see what it does because in fact it uses these three blocks, and that's interesting to understand how GFSK demodulation works on a digital system. And the code is quite well documented and it's quite nice. For example, it gives you the explanation about the gain you've got to to put in here according to the number of samples per symbol you've got. And of course, something really important in digital communication is to have the right rate. So you've got a clock recovery system. It uses the algorithm from Muller and Muller. It's very well known. It's a publication that you can find easily on the internet, and it's quite interesting. It's not so complicated to understand that. After that, you've got a binary slicer. So just to transform what gets out here into 0 and 1s. And the Nordic RX block, if you look into the code, it gets the 0 and 1, builds again bytes, and after that, it tries to recover a packet. Okay? And then it prints it via the Nordic type printer block.
So the preamble is detected in the Nordic RX block then, from the bits to.
Here you've got a message which is a PMT with the information about what's inside the packet, the address, etc. And that's what is printed like here.
Okay.
Okay?
But the preamble and the address are all both 555. So if you have a distortion in the beginning, then you might see part of the address as the preamble.
Correct. Sometimes it doesn't work. It's possible. That's why, using sequences like that, sending several times the packet, or using something about a bit more sophisticated. You send the packet, you ask the receiver to send an acknowledge. So you have to do that if you want to have a secure communication. Yeah.
I mean, there's a CRC, of course, so the CRC doesn't match then.
Exactly, CFC, the CRC is exactly here for that. So if I launch my model, I should get something working. Well, I had some nice things. The squelch block adds tags, which are squelch start of block and squelch end of block, and you can synchronize your time plot with this tag. Do you know how to do that? How to synchronize with a tag? Okay, I'll show you. So that's my GFSK packet. Okay. So yeah, what you can do is simply you go here. You've got trigger, okay, and my tag is squelch underscore SOB. So I say I want to synchronize on the squelch SOB. That's quite nice because you see exactly what you want to see and not the rest. Okay? Or sometimes you lose packets, that's possible. Huh? Okay? So you've got this model, you can use it if you want. Yes?
The Nordic print, but this is installed. Also, include XML model.
Has no module object, has no attribute. Python, the Python file in the Python directory. Yeah. Okay. Donc, have a look first on this one.
Yeah, just override the file.
From Nordic blocks, yes, that's correct. Okay, so that's good. The CMake list, okay. Nordic blocks, yeah, that's fine. And then after that, I was thinking about the other one. Can I see your in the Python library again in Python directory the Nordic blocks? Okay, so Nordic, can you go down?
So in order file I have to comment this, no? Because with the string give me some errors.
Yeah, that we don't use it anyway, so this is not a problem. Yeah. So go to the end of file just to see that everything is right. It's okay. No, that seems to be fine. You did after that again a build.
Yeah, because the new blocks appear.
Okay.
So
No, it's just I don't know what. Maybe okay, maybe like I mean,
Just save Nordic printer, Nordic printer. Ah, it's the attribute error. Oui, c'est pas grave, tu le commentes. Ouais, exact. Sinon, on aurait pu l'installer parce qu'en fait, il suffit de faire un SU et puis ensuite un apt-get install Python, machin, et c'est bon, quoi, il l'installe, quoi. Ouais, exact, ouais.
Il faut le recommander là, puisqu'il ne l'utilise pas en fait.
Oui, il ne l'utilise pas de toute façon. Hein. Non, non, c'est clair, ouais, parce que autrement, on va se retrouver effectivement avec le même souci, quoi.
Il faut faire du copier-coller.
Bah, soit tu passes 8 heures à taper tout le code, soit...
Non, mais parce que là, en retapant les trucs, il a oublié des lettres.
Bon, faut dire que la Debian comme ça, moi j'ai un peu du mal. Hein, il manque de petites fonctions graphiques venant d'Ubuntu.
C'est pas évident, mais c'est vrai que soit on passe du temps à débugger.
Mais c'est ça en fait. Okay, everybody, you've all understood what we did? Are you stuck in a step or? Yeah, no, the tab printer is empty. Yeah. It's the init that's good. That causes the problem. Perhaps. Oh yeah. Can you go again in the Python file?
This is actually generated, no?
The one that defines the block. Inside the GNURadio, the Python. If you can, this one, if you can open it again. Yeah, comment this bit string. And rebuild again. You see. C'est bon tout le monde là ou?
J'ai un problème il manque, il n'arrive pas à trouver.
Il n'arrive pas à trouver.
Nordic tape printer.xml.
Le point XML, il n'arrive pas à le trouver. Alors, on va voir ça. Donc c'est dans GRC, vous avez modifié le CMake. Ouais, Nordic, il s'appelle bien Nordic _ Nordic Tab Printer, parce qu'il faut qu'il soit là. Bah il n'y est pas. Hein. Ah bah ouais, faut le mettre.
Et il est dans les steps?
Mais parce que le GRC, il se met pas dans GRC. Hein. C'est vrai que c'est un peu perturbant, mais GRC, c'est un graphe comme ça et ça se met pas dans le répertoire GRC. Ce qu'on met dans le répertoire GRC, c'est que les définitions des blocs en XML en fait. Et là, il vous manque précisément, c'est pour ça qu'il râle parce qu'il l'a pas. Hein,
il est dans steps du coup?
Ouais.
Okay.
Donc c'est juste ça. Hein.
Et du coup, celui-là,
Celui-là, faut le mettre, vous le mettez par exemple dans GR Nordic à la racine, hein, ou sur votre bureau, peu importe. Hein. D'accord?
Et puis du coup, moi j'avais une autre question, c'était par rapport au CMake. On faisait CMake point. Du coup, si...
point, ça veut dire qu'on monte d'un cran. Mais parce qu'en fait, le fichier CMake, en fait, qu'on utilise, il est un cran au-dessus de build, puisqu'on crée un répertoire build. Donc le fait de faire CMake point, ça veut dire il va exécuter CMake à un répertoire au-dessus.
Okay.
C'est pour ça. Voilà. Ouais. Et maintenant, il faut faire la compile et puis ça ira. Hein. Ça marche? Oui, le RX.
Faut qu'on le fasse, le RX, c'est ça?
Oui, ben enfin, ou tu regardes dans la doc, enfin dans le V4, je ne sais plus maintenant dans quel numéro j'en suis.
c'est ça?
Oui, je faisais la boucle après. Hein.
Le 5, c'est le TX.
Oui, le TX, ben en fait je parlais du RX là, parce que c'était le récepteur, c'était valider le récepteur avec les blocs maintenant qui étaient présents, quoi. C'était ça l'idée.
Du coup, il n'y a pas de RX dans les V en fait. C'est ce que je veux dire.
Si, NRF24, receiver, puisqu'ils l'ont à côté. Alors c'est le V4 ou le V... Vas-y, celui d'avant.
Ah oui, non.
Ah, je croyais que j'avais oublié, mais c'est bien. Ok. Ça marche. Ah non, c'est bon, ça marche tout seul.
Tout marche.
Ouais, c'est nickel. Bah, comme quoi, il faut le faire une fois et puis.
C'est celui-là qui est enregistré, donc c'est bien.
Cool. Yeah. Okay.
The RF bandwidth is set to 1.5 megasamples, but the sample rate is at 4 megasamples. So are you doing like zero padding or something, or interpolation?
No, in fact, for a receiver, I always try to take more samples than what I do at the transmitter. Well, that's what I did with GNURadio. Most of the time, for a digital system to work well, you use for a symbol at least 8 samples.
Okay.
That's a rule of thumb. Okay. So that's why I did that.
Okay.
Because my transceiver, I don't know exactly how the chip works, but for sure it's gonna use more than 8 samples.
Yeah.
Because it's analog, in fact. Okay.
But over here we are receiving, and
yes,
and it's just like doing a rational interpolation.
Yes.
What we are doing,
Yeah.
well, fractional interpolation 1.5 for.
Yeah, and taking more symbol, for example, for the clock recovery is normally much better as well.
Okay.
When you take more samples. Of course, you're not gonna take 100 samples,
Yeah.
but you know a rule of thumb is more than 4 between 8.
Okay. Okay. That's
Okay.
Yeah. Okay. Thanks. Yeah.
It works?
It's working. I'm getting something, but I don't. We still have to decode it.
Okay, fine. C'est quoi le deadline? C'est jusqu'à quand? On a encore combien? C'est fini. Okay. Normally it's finished. My colleague said that. Jean-Michel, c'est... Je sais pas, j'ai encore quelques minutes. Ouais, ok. Donc je dispose de combien de temps à peu près, juste? Cool. Ok. Ok. Let's go for the next. So again, what we've done now, we've got all the blocks for the receiver inside GRC. What would be nice now is to have the same for the transmitter. Okay. So the transmitter is going to be a bit tougher because we are going to use the PMTs. Okay. Well, a few things about GFSK. I put that in the slides. So since we haven't got much time, you can look at it. You have the slides. Okay. So I just summarize, and it's interesting just to see how they've done it, because that's the theory. Okay. But the nice thing is, how do you implement it in the digital domain? Okay. And that's this information you're gonna find in the gfsk.py. Okay. Same with the receiver. It's a phase shift discriminator. Okay. And how do you implement that? Well, using this structure. It's quite nice. When you read the code, you find that they've done like that. Okay. So it's interesting to read codes like that, because of course you understand the way that you can do it digitally.
Is this a subsample delay or is this a single sample delay?
It's a single sample delay.
Single sample.
Yeah, yeah. So I've added also something if you want to connect this to Wireshark, because you see you had your packets, but at the same time it sends to a UDP port the results, the decoded packet. So with Wireshark, they've implemented a Lua script that allows Wireshark to see the packets, decoded packets, directly from the Nordic Tap printer. Because we've seen what Nordic Tap printer did in the terminal, but more of that, it sends also to UDP port the packet. And these are the commands that you can use to see that in Wireshark. Okay? So it's quite nice. They've done an interesting work with this OOT module. So now a bit more tricky thing is that the message passing interface uses the PMTs. And in fact, what I have understood about the utility of PMTs is that, well, in fact, it's quite logical. From a programming perspective, a message can be represented as a data type, simply, okay? When you are in Python, it's not a problem because it's really weakly typed. So for Python, you know, no problem. Whereas for C++, as it is strongly typed, you have to be careful about the types. So PMTs is just an answer to this problem, okay? So it allows to exchange data types between Python and C++, okay? So these data objects, you have got a nice page on the GNURadio website. And if you want to know more about PMTs, the dictionary, and the way it works, it's really well written because most of the time people criticize the fact that you haven't got a lot of tutorials, it's not well explained, but in that case, you know, they've really done a nice job. So I encourage you to go and see the things about PMTs. So now, oh, what is he doing? Okay. So the transmitter. What we see if we study the block Nordic transmitter, Nordic TX, okay, the message, the input has to be a PMT, and the PMT has to have these data in this way. So for us, channel index, when we've got only one channel, is 0. The channel number, 85. The data rate, 2. The address length, 5. The payload length, 8. The header seconds number, 0. No acknowledge, 0. In that case, the CRC, we use 2 bytes, the address, and the payload. So we would like exactly to mimic what the STM32 does with this transmitter. So the easiest thing to do with this Nordic tap, we'll have to add this block again. It's a new block. So I'll show you if I find my, it's not this one. I've closed it. Tick, tick, tick. I've closed it. Open. I'm still working behind the scene. Okay. It's TX, yeah, it's this one, okay. So remember, the input of the Nordic TX block is a message. So what you can do is to use simply the message strobe block, and you initialize the PMT with the values I've just shown, okay? That's the easiest way to do it. And you mimic exactly what does the STM32. That's not the final thing because I use, why do I have to use, yeah, that's an important point. Why do I have to use a message strobe? Do you know why? If you look in the code they've done, it's a loop, a never-ending loop, and they send packet like that. And that's not something that you should do. I want to send a packet every 1 second or half a second. So the message strobe is just a thread that's working, and every half a second, it sends a message. And that's exactly what we want. So it's existing, and we're going to use it, and it's interesting.
Because the user P has his own clock domain. This is the clock domain I'm coming from the PC every millisecond because it's scanning of a thread. Like
Yeah,
domain.
that's
and
right.
The other one is probably something which pulled from an ADC clock.
Yeah, in fact, the message strobe block, it's the PC clock. It's the
PC clock, right?
yeah. And you see, you have to be careful about the syntax. So it's a PLT init. It's a U8 vector. Okay, you have to indicate the length of the vector, and the packets vector, which is initialized just here. Okay. So I wasn't satisfied with this, so I carried on with another block, which I found again in the examples. Finally, oui, ça fait au moins 5 fois que je le perds. Je devrais l'accrocher plus. Ça va pas être bon pour l'enregistrement. Alors. That's again terrible. This mic. Put it somewhere else. You see the difference with this one? That's the final one. I've just added a Nordic tap transmitter, and it's easier to play with a block like that because I don't have to have variables, you know, with. I just have to initialize my address, my payload in a normal way, and you know, to trigger. Of course, I've got my message strobe, and it works pretty well. Yeah, I just have to enter my message here, channel and everything, and you know, in a friendly way. Exactly, and this works fine for that. So that's the final thing. You've got everything in the zip. So okay, so that was V5 and V6. Okay. So I gave you almost everything to. Yeah. After that, I've added a tag because I wanted to synchronize my display with the start of the packet. So I added a part in the code, the C++ code. I just added a tag which has the length of the packet. But you have to be careful about that because your packet is, for example, 36 bytes long. But when you go into the digital domain with the modulation, upsampling and all this, your length has to change. So it would be nice to have something that increase your length you have at the beginning. And for that, you have something really interesting. It's the GRFU. 3 minutes, okay. And this burst tagger block, so you have to install this library. It's you know that you've got 8 bits in a byte, so multiplied by 4 because I take 4 samples. At the end, I must multiply by 32. So I will have exactly the size of the packet in samples after the modulation. Okay, and that's the burst tagger block. And I finish with just one thing if you want to try. And it's the conclusion. This was just an introduction to packet communication, but you've got a nice list of different OOTs to test with packets, and people like Tim Oshie have gone quite far with that. For example, GR even stream, it demodulates the signal only when you've got an event, and this event is the power you calculate at the input of your receiver, and all the data processing is done only when something comes in. And that's really efficient in terms of speed, okay? And look also at this one. That's a student from EPFL, and it's really nice the work is done about packet communication in GNURadio. And if you want, also, you've got a dongle, the dongle I was talking about. You can flash the firmware of your dongle, and you can try to sniff people having the same type of mice, and you can see exactly the packets going. And it can become also a transmitter in the 2.4 gigahertz. It sends simply a tone on the 2.4 gigahertz band. So funny things to look at. So I've finished. Thank you very much for your attention. I'm still very hot. Oui. Just a last thing. Everything's going to be put on my website, the modified module, okay, and everything. Yes. And even how to fiddle with the dongle, if you want to try it. Yes. Okay?
Yes, that's very good. Thank you. Because we need more time.
Yeah, sure.